Hello everyone. So in this video, I'm going to talk about more than 30 problem types that can be asked from the chapter Ray Optics. So we have come up with this detailed analysis where we have categorized previous year's JEE Mains questions as problem type. And I guarantee you won't find this kind of a detailed analysis in a short video anywhere on internet. So it is highly recommended for you to watch this video till end so that whatever questions come from this chapter, you'll be able to crack that in JEE Mains 2025. Now let us see who will get benefited from this video. So if you know basics and your NCERT level knowledge is fine, but you are struggling with the numerical part, so this video is for you. And if you've done the same chapter in your coaching, but still you are struggling with the numericals, so this video is for you. And how you can use this video effectively? First, you have to revise the short notes which you have prepared for this chapter. Then whatever important information you come across, write down that important information in your notes. And whenever I discuss any problem, you have to pause the video and try to solve the question on your own. Now if you look at the syllabus, so this is the syllabus. You can just pause the video and just focus on this. And now we can directly jump to the different problem types. So from mirrors, like plane mirrors and spherical mirrors, so we're going to see 10 different problem types. So these are 10 different problem types. So I'm going to discuss each problem type one by one. Now the first problem type is based on the nature of the image formed by the plane mirror. And you must have studied this in your class 10th, right? So first of all, if you look at the properties of the image formed by the plane mirror, the size of the object is same as the size of the image. And if you look at the second property, the image will be erect. Right, if we have an object AB, then the image will be A prime, B prime, both are erect, and the image will be laterally inverted. Right, if you have your, if you look at your left hand in the mirror, it looks like a right hand. So there will be a lateral inversion. So these are the three important properties that you have to keep in your mind. Now let us the question based on this property. An object is placed at a distance of 12 centimeter in front of the plane mirror. The virtual and the erect image is formed by the mirror. Now the mirror is moved by 4 centimeter towards the stationary object. So we have given a stationary object. Let us say this is the object AB. And this is the mirror. And it is placed at a distance of 12 centimeter from the mirror. So its image will be formed at a distance 12 centimeter behind the mirror. So if I show the image with red color, so this is the image, A prime, B prime. And this distance is also 12 centimeter. Now the mirror is moved by 4 centimeter towards the stationary observer. Now we are moving this mirror. Now it has moved by a distance of 4 centimeter towards the object. So this distance is 4 centimeter. Now the distance of the object from the mirror will be 12 minus 4, that will be 8 centimeter. The distance by which the position of the image would be shifted. Now we have to find the image position, right? So now the object is at a distance of 8 centimeters, so the image will be formed 8 centimeter behind the mirror. So that will be the new position. Let me call this as A double prime, B double prime. And this distance will be 8 centimeter. Okay, so now we have to find the distance moved by the image. So basically we have to find this distance x. So if you look at this diagram, so what we can say, 8 plus x should be equals to 12 plus 12, right? So from this, x is equals to 24 minus 16, so that comes out to be 8 centimeter. And it is moving, image has moved in the left direction towards the mirror, right? So it is 8 centimeter towards the mirror. So option 2 is the right answer. Now let us see another problem based on the same concept. The light ray from an object have been reflected towards an observer from a standard flat mirror. The image observed by the observer are real, erect, smaller in size than object, laterally inverted. Choose the most appropriate answer from the options given below. So we know that plane mirror always forms an erect image and the image will be laterally inverted. So option, and it will be virtual, right? So B is correct. Small in size than object, that is incorrect, right? So B and D are the right options. So answer will be option option 1, right? So that is the answer. Now let us see the next problem type, and it is based on the angle of deviation. So deviation produced by the plane mirror. So if there is a incident ray, and this is the incident ray, this is the reflected ray, and this is the normal at the point of incidence. So the angle, so the angle made, or you can say the angle by which the incident ray has deviated from its original path. So we can say this angle will be the angle of deviation, and angle of deviation will be given as 180 minus 2 times the angle of incidence. So this you can remember, right? Okay, right. So let us see a question based on this concept. When one light ray is reflected from a plane mirror with 30-degree of angle of reflection. So we have given a plane mirror. An angle of reflection is given to us. This angle is given as 30 degrees. Obviously, the angle of incidence is also 30 degrees, right? And we have to find the angle of deviation. So angle of deviation will be 180 minus 2 times the angle of incidence. So it will be 180 minus 60 degrees, which comes out to be 120 degrees. A very basic question. So option 2 is the right answer. Right. So now let us see one more question based on the same concept. A light ray is incident at an angle of theta 1 on the system of two plane mirrors M1 and M2 having an inclination angle of 75 degrees. So the angle between the mirror is 75. After reflecting from the mirror M1, it gets reflected back by the mirror 2 with an angle of reflection 30. So let me just show you the diagram. So it is this is the reflected ray by the mirror 1, and the reflected ray by the mirror 2 makes an angle of 30 degree with the normal. So this angle is given. So we have to find the total deviation produced in the ray. So here you have to add up the deviation produced by the mirror 1 and the mirror 2. So if you look at the deviation produced by the mirror 1, we can say this total angle will be the deviation produced. So that will be delta 1, let us say. And it is and this deviation is being produced in the anti-clockwise direction, right? So let us take anti-clockwise as positive. Now the deviation produced by the second mirror M2 will be this, right? Delta 2. Again, this deviation is also anti-clockwise. So we can say the net deviation will be delta 1 plus delta 2. So we have to find the value of delta 1 and delta 2, and then we can plug those values in this formula, we'll get the answer. So right, so we have given 30 degrees. So we can see the angle of incidence on mirror 2 is also 30. So this angle is 30. So we can say this angle will be 60 degrees, right? Because normal makes an angle 90 degree with the mirror. So this is 60, this is 75. So we can say this angle will be 75 plus 60 is 135. So this will be 45. So what we can say, if I draw a normal to the mirror 1 at the point of incidence, then this angle is also 45. So this angle is 45. So the angle of incidence is also 45. Right, so we know the angle of incidence at mirror 1, we know the angle of incidence at mirror 2. So we can say the deviation produced by the mirror 1 will be 180 minus 2 times the angle of incidence, which is 45 degree. And the deviation produced by the second mirror will be 180 minus 2 times the angle of incidence, which is 30 degrees. So this comes out to be 90, and this comes out to be 120. So if we add up these two deviations, it comes out to be 90 plus 120, which is 210. So 210 degrees is the answer of this question. Right, so let us see the next problem type, and it is based on the rotation of the mirror. And right, so if we rotate a mirror for a given incident ray, let us say we have rotated the mirror in the clockwise direction by an angle theta, the reflected ray will rotate by an angle delta, let us say. So this delta comes out to be 2 times the theta. And the rotation in the reflected ray is also in the same direction. If you rotate the mirror by clockwise, then the reflected ray will also rotate clockwise by twice the angle. So this you have to remember. So that is the question based on this illustration, in this problem type. A beam of light from a source L is incident normally on a plane mirror fixed at a certain distance x from the source. Let us say this is the source L, and the ray is hitting normally on a plane mirror. When the mirror is rotated through an angle, so if I show the ray, so ray was hitting normally, so it will retrace its path. So when the mirror is rotated through an angle small angle theta, okay, right, so the beam is reflected back as a spot on a scale placed just above the source L. Okay, right, so there is a scale which is placed just above the source, so we can say the spot will be somewhere here, right, when it is hitting normally. When the mirror is rotated through a small angle theta, the spot of light is found to move through a distance y on the scale. Okay, right. So now when we rotate this mirror, let us say the mirror has been rotated by an angle theta in the clockwise direction. The reflected ray will also rotate. Now let us, this is the reflected ray. And this spot has moved by a distance that will be y, right? So this is y. And the distance of the object of the mirror from the source is x. So we have to find find theta in terms of x and y. So we know that the reflected ray will rotate by twice the angle, right? So it will be 2 theta. Now in this right angle triangle, we can say tan 2 theta is equals to y by x perpendicular upon base, and we have given that that angle is very small. If angle is very small, tan 2 theta can be written as 2 theta. So from this theta comes out to be y by 2x. So option 4 is the right answer. Now let us see the next problem type, and it is based on the concept of field of view. And what do we mean by that? Suppose there is an object and there is a mirror, and the image is being formed by the mirror. If you want to see the image of the object, you have to be placed in certain region so that so you will be able to see the image. So that region is known as the field of view. For example, if I consider incident rays at the extreme of the mirror, and these are the reflected rays. So I can say the area bounded by these reflected rays will give us the field of view, because if you are placed in this region, you will be able to see the image of the object. For example, if you are placed here, so there will be a ray which is getting reflected from the mirror, and this ray and the reflected ray is getting into your eye, and you will be able to see the image. I hope this concept is clear. Now let us see the question based on this concept. A point source of light S placed at a distance 60 centimeter in front of the center of a plane mirror. So this source is placed at a distance 60 centimeter from the plane mirror. Plane mirror it's a finite plane mirror which is having a length 50 centimeter. Hangs vertically on the wall. A man walks in front of the mirror along a line parallel to the mirror, right? So this is the line which they are talking about, parallel to the mirror, at a distance 1.2 meter from it. And this line is at a distance of 1.2 meters. The distance between the extreme points where he can see the image of the light source in the mirror. So basically they are talking about the field of view only. So if I consider incident rays at the extreme, so this is the reflected ray. Similarly on the other extreme, then this is the reflected ray. So if the observer is located, say let me call this point as A and this point as B, and let me just join these 2 points. If the object is located anywhere on the line segment AB, he'll be able to see the image, because AB line segment lies in the field of view. So we have to find this. So what we can do, we can use similar triangles here. So let me just draw this. Right. So if this angle is theta, then we can say this angle is also theta. Right. Now this small triangle is similar to this big triangle, right? Where this side is half of 50, that will be 25 centimeter. and let us say this side is x, right? And this is 60, and this total distance is 1.2. So if we compare, if we take the ratios, so we can say 25 x by 25 will be equals to 1.2 by zero point 0.6, right? So I've converted 60 centimeter into meter, so this comes out to be 2. So x comes out to be 50 centimeter, right? So x is 50. Similarly, we can say this length is also 50 centimeters, and this length will be nothing but 50 centimeter. So what we can say, the length of the line segment AB is 150. So that will be 50 times 3, that will be 150 centimeter. So that is the answer of this question. The next problem type is based on the vector form of law of reflection. So we know what is law of reflection, right? If there is a shiny surface and there is an incident ray, the angle of incidence will be equals to the angle of reflection. Now in this vector form, if we have given incident ray direction, I cap is the unit vector along the incident ray, n cap is the unit vector along the normal, and we want to find what is r cap. R cap is the unit vector in the direction of reflected ray, then we can use this relation. R cap will be I cap minus 2 times n cap dot I cap times n cap, right? So do remember this relation. So let us the question based on this concept. The incident ray, reflected ray, and the outward normal drawn to the normal are denoted by the unit vector a, b, c. So basically they have, instead of I cap, they have taken a cap, and instead of r cap, they have taken b cap, and for normal n cap, they have taken c cap. The choose the correct relation. So if you look at this relation, it is nothing but option 3, right? So option 3 is the right answer. A cap, b cap will be a cap minus 2 times a dot c times c cap. Okay, now let us see the next problem type, and it is based on the image formed by two parallel plane mirrors. So let us understand this concept with an illustration. So here we are given an object which is placed at a distance of 2 centimeter from the left mirror. So we have a mirror M1 on the left side, M2 on the right side, and the distance between these two mirrors is 10 centimeters. So this distance is 10 centimeters. Now if we consider first reflection happening at mirror 1, then the image formed by the first mirror will be at a distance of 2 centimeter. So this distance will be 2 centimeter, because the object is at 2 centimeter from the mirror. Now this image by the mirror 1 will act as the object for the second mirror. Now if this is the object for the second mirror, we can say now the object is placed at a distance of 10 plus 2, 12 centimeters. So this distance will be 12. So the image will be formed 12 centimeter behind the mirror. So this distance is 12, right? Now this image formed by the mirror 2 will act as the object for the mirror 1. Now this object is placed at a distance of 10 plus 12, which will be 22 centimeters. So the image formed by the mirror 1 will be 22 centimeter behind the mirror, right? And this phenomena will keeps on happening. So this is the phenomena when we are considered the first reflection with the mirror 1. The same phenomena can happen if we consider first reflection with the mirror 2. Now what you have to remember, so distance of image formed by mirror 1, and let me write here distance of image formed by mirror 2. So the first image formed by mirror 1 is at 2 centimeter from the mirror, and the first image formed by the mirror 2, if I consider first reflection with the mirror 2, it will be 8 centimeter. Now what you have to do, you have to add 10 to 2. So if I add 10 to 2, I will get 12, right? And if I add 10 to 8, I will get 18. So you have to keep on doing this, right? And you will get the different positions of the images. Then we'll get this will be 28, and then this will give us 22, then 32, and this will be 38. Okay, so this will keeps on happening. So that is the image of the first that is the closest image to the mirror one, and that is the next closest image, right? 18, then 22, then 38. So this you have to remember. Now let us see the concept based on the same problem type. Two vertical plane mirror A and B are separated by 10 centimeter, and object O is placed at a distance 2 centimeter from the mirror A. The distance of the second nearest image formed behind the mirror A from the mirror A. So if I show the image formed by the mirror A and the image formed by the mirror B, so the first image will be at 2 centimeter, and for the mirror B it will be 8 centimeter. Then if we add 10 to 2, it will become 12 centimeter. This will become 18 centimeter, and then 28 centimeter, and this will be 22 centimeter. And they're asking about the second image formed by the mirror A. So the answer will be 18, right? Now let us see the next problem type, and it is based on the image formation by the spherical mirrors. So there are two types of spherical mirrors, concave and convex, and you must have studied about these in class 10th. Now let us see the different cases in case of a concave mirror. Now if the object is placed at infinity, then the image will be formed at the focus, and it will be a real and inverted image, highly diminished image, right? So it will be at focus, highly diminished, real and inverted. Now if the object is placed beyond center of curvature, then the image will be formed between the center of curvature and the focus, and it will be diminished, again the real and inverted image. And if the object is placed at the center of curvature, then the image is formed at the center of curvature only, and it will be of the same size, and it will be real and inverted, right? Now if the object is placed between center of curvature and the focus, then the image will be formed beyond C, and it will be enlarged, and it will be real and inverted. Can you see? It is real and inverted, and it will be beyond C. And if the object is placed at the focus, then the image will be at infinity, and it is highly enlarged image, and again it will be real and inverted. But if the object, so this is the case when the object is at focus, right? If the object is at between the focus and the pole, in this case the image will be behind the mirror. We'll get a virtual and erect image, magnified image, right? Enlarged image, and the image you can say is and it will be virtual and erect. So this table you have to remember. Now let us see the image formation formed by the convex mirror, right? So in case of a convex mirror, there are two cases. First case is when the object is at infinity. In this case, the image will be formed at the focus, and it will be virtual and erect, highly diminished point sized image. Now if the object is placed between the infinity and the pole, then in this case the image will be formed between the pole and the focus. Can you see? Image is being formed between the pole and the focus, and it will be diminished, and it will be virtual and erect. So convex mirror will always form virtual and erect image, and it will be diminished. So that's why we use convex mirror as a rear view mirror in our vehicles. And also we okay, right? So and if you look at this particular case, the last case when the object is between the focus and the pole, this case we use in the shaving view mirror, where we want to see the enlarged erect image of the object. Now let us see the questions based, and okay, right, one more thing that we have to remember is the mirror formula. So what is mirror formula? It will be 1 by V plus 1 by U is equals to 1 by F, where V is the position, or you can the distance of the image from the pole, and U is the distance of the object from the pole, and F is the focal length of the spherical mirror, where focal length is R by 2, where R is the radius of curvature of the mirror. And if I talk about the magnification, will be given as minus of V by U, right? So this you have to remember. And also, like whenever you apply these two formulas, you have to apply put values as per the proper sign convention, right? For example, if all the distance is measured in the direction of incident rays, suppose if this is the concave mirror, and suppose we want to measure this distance. So to measure the distance of 0.1, let us say, we have to travel, and let us say this is the direction of incident ray. So we have to travel in the right direction along the direction of incident ray. We'll take this distance as positive. And suppose if we want to measure a distance against the direction of incident ray, suppose if we want to measure a distance of 0.2 from the pole. So in order to measure that, we have to travel in the left direction, which is against the direction of incident ray. We'll take that as negative. And if you are going above the axis, we'll take this distance as positive. And if you're going down the axis, we'll take this distance as negative. Okay, so these things you have to keep in your mind. Now let us see some illustration based on this problem type. A convex mirror of radius of curvature 30, so this is R, forms an image that is half the size of the object. So the size is diminished and the object distance is, and it's a convex mirror. So we know that in case of a convex mirror, we'll always get a diminished image, right? And we have to find the distance of the object. So we have to find U. So focus, let me draw the diagram. So that is the convex mirror. This is the principal axis, and radius of curvature is given as 30 centimeter. And the incident ray is in the right direction. Incident rays are going in the right direction. So we can say this is the center of curvature. So R will be positive. So focal length is also positive. So focal length will be R by 2. So which comes out to be 15 centimeter. So now we know what is the focal length, and we know the size of the size of the image is half of the size of the object. So we can say height of the image is half the height of the object. And we know that magnification is nothing but height of the image divided by height of the object, and this is minus V by U. Right, so we can say magnification is given to us as 1 by 2. Okay, and it should be positive. Magnification will be positive because we are getting the erect image of the object. So 1 by 2 is equals to minus V by U. So V is minus U by 2, right? So we got the relation between V and U. Now we can apply mirror formula. So 1 by V can be written as minus U by 2 plus 1 by U equals to 1 by F, which is 15. So from this, it will be minus 2 plus 1 by U is equals to 1 by 15. And from this, U comes out to be minus 15 centimeters, right? So option 1 is the right answer. Now let us see the next question. If the distance between the object and its 2 times magnified virtual image, so magnification is given as 2, produced by the curved mirror is 15 centimeter, the focal length of the mirror must be, okay, right? So we get a magnified image either only in case of a concave mirror, right? Because in case of a convex mirror, we'll get a diminished image. So we are getting magnified image. So it is a concave mirror, and the object is being placed, and it is a virtual image, right? And the object must be placed between the focus and the pole. So magnification will be positive only. And we can say minus V by U is equals to 2. So V is minus of 2U. So and what we have given, if the distance of the object from and it's 2 times magnified virtual image. So this is the distance of the object. So that is U. Sorry, this is not U. U is the distance between the object and the image. So let me draw the diagram. So we have given a concave mirror and there is an object, and we are getting a magnified image of this object. This distance is given as 15 centimeter, right? So what we can say, if this is X and this is V, then X plus V is 15, or U can be written as minus of X, right? Now from this, V, which is 15 minus X, can be written as minus of 2U, because 15 minus X will be minus of 2 times, what is U? U is minus X, right? So from this, we'll get 3X equals to 15. So X comes out to be 5 centimeters. So X is 5 centimeter. and we have to find the focal length, right? So let us apply mirror formula. So 1 by v plus 1 by u is equals to 1 by f. So 1 by v is v in this case v will be 15 minus x, so v will be 10. So v is 15 minus x, so it will be 10 centimeters. So 1 by 10 plus x is 5, so that will be minus x, which is minus 5, and the focal length we have to calculate. So this comes out to be, so 1 minus 2 by 10, so f comes out to be minus 10 centimeter. Since we are getting negative focal length, so we can say it's a concave mirror. So answer is minus 10. So option 3 is the right answer. Now let us see the next problem. Two objects A and B are placed at 15 centimeter and 25 centimeter from the pole in front of a concave mirror, having the radius of curvature 40. The distance between the image formed by the mirror. So we have to find the image of A and B, and then we'll have to find the distance between them. So if we consider A, so we have a concave mirror, and this is the direction of incident ray, so we can say focal length will be negative, so that will be nothing but minus of 40 by 2, because radius of curvature is 40. So this will be minus 20 centimeter. So we have given a position of the first object A, so that is the object A which is placed at a distance of 15 centimeter. So u will be minus 15 centimeters. So 1 by v is equals to 1 by f minus 1 by u. So 1 by minus 20 plus 1 by 15. So LCM will be 60. So minus 3 plus 4, that will be 1 by 60. So v comes out to be 60 centimeter. Right? Now if I want to find the position for B, so in this case u is minus 25. And focal length is minus 20, because we are talking about the same mirror. So 1 by v is equals to 1 by f minus 1 by u. That will be 25. So LCM will be 100. So minus 5 plus 4. So v comes out to be minus 100 centimeter. Okay, so if you look at, if I show this on the same principal axis, this is the principal axis, this is the mirror. So the first image is being formed at plus 60. So that will be plus 60 centimeter. That is the image of A. And the image of B is formed at minus 100. Minus 100 is in the left direction, right? Against the direction of incident ray. So this is the image of the second object. And this is 100 centimeter. So what is the distance between the image of A and B? It is 100 plus 60, that is 160. So option 3 is the right answer. Now let us see the next problem. A short straight object of height 100 centimeters. So height of the object is given as 100 centimeter. Lies before the principal axis, lies before the central axis of the spherical mirror, whose focal length has an absolute value. So focal length is given as 40 centimeter, and they have not mentioned which type of mirror they're talking about. The image of the object produced by the mirror is of height 25 centimeter and has the same orientation of the object. So it means we are getting an erect image. So height of the image is 25 centimeter. And when do we get erect image, and which is diminished, right? So in case of a concave, we'll get a erect image, but that is magnified. So it means the mirror is not concave, it is convex. We are getting a diminished image. Has the same orientation. On one may conclude from the information that this image will be virtual, erect, diminished, and the mirror will be convex. So let us see the option. So image is virtual, opposite side of the convex mirror. So virtual, in this case, it is image will be formed on the other side of the mirror. So option 4 is the right answer, right? So this is incorrect, this is incorrect. Image is real, so that is also incorrect. So option 4 is the right answer. Now let us see another illustration. An object O is placed at a distance of 100 centimeter in front of the concave mirror. of radius of curvature 200 centimeter. The object starts moving towards the mirror with a speed of 2 centimeters per second. So let us say this distance is given as 100 initially, and this object is moving in the right direction with 2 centimeters per second. The position of the image from the mirror after 10 seconds. So after 10 seconds, if you want to find the position of the image, we should know what is the position of the object. So in 10 seconds, distance covered by the object will be what? So speed is 2 centimeters per second, distance is time is 10. So the distance covered will be 2 times 10. It will be 20 centimeter. So what we can say, if it is 100 after 10 second, let us say O prime is the new position. Its distance from the pole will be 80, right? It will be 80 centimeters. So we can say U will be minus 80. And focal length is not given, and we have to find the position of the image. Radius of curvature is given, right? That is 200. So focal length will be minus 100 centimeter. So 1 by V is equals to 1 by F minus 1 by U. So that will be 1 by minus 100 plus 1 by 80. So LCM will be 400. So minus 4 plus 5 will be 1 by 400. So V comes out to be plus 400 centimeter. So we're going to get a virtual and erect image, and the position will be 400 centimeter behind the mirror. So it should be 400, right? Now let us see the next problem type. Again, it is based on the image formation by the spherical mirror. But in this case, the object, we have an extended object which is aligned with the principal axis. Right. So in this problem, let us see this illustration. So we have given an object AB, where A is at a distance 40 centimeter from the pole and B is at a distance of 60 centimeters. So 20 plus 40. So the length of the object is 20 centimeter. B is aligned with the center of curvature, and we need to find the magnification or the size of the image, right? So if you see the image of A by using mirror formula, it is formed at 120 centimeter, right? So image of A will be at 120 centimeter on the left side. And if you consider the image of B, it is formed at center of curvature only. Now what is the length of the image? It is the distance between A prime and B prime, which is nothing but 60 centimeter. So the length of the image will be 60 centimeter. And if you look at the orientation, so we have BA, B in the left side, A is in the right side. But if you look at the image, it is inverted, right? So if we have an object BA, we are getting A prime, B prime as the image. So if you talk about the longitudinal magnification, then longitudinal magnification will be defined as minus of size of the image upon size of the object. So the length of the object is 20 and length of the image is 60. So the answer will be minus 3. I hope this is concept is clear. Now let us the illustration, the question which came in JEE Mains based on this concept. A thin cylindrical rod of length 10 centimeter is placed horizontally on a principal axis of a concave mirror of focal length 20 centimeter. Let me just draw the diagram. So we have given a concave mirror, and this is the center of curvature, C, and the length of the rod is 10 centimeter and focal length is 20 centimeter. So we can say the center of curvature will be at a distance of 40. The rod is placed in such a way that the midpoint of the rod is at 40 centimeter. So there is a rod and the midpoint is at 40 centimeter and the length of the rod is 10 centimeter. So it means this point will be at a distance of 35 centimeter and the other end will be at a distance of 45 centimeter. The length of the image formed by the mirror will be x by 3 centimeter. What is the value of x? So again, we have to find the length of the image. So if I consider this point as A and this point as B, let us find the positions of A and B. So for A, U will be minus 35 f is minus 20. So we can say 1 by v is equals to 1 by f minus 1 by u. So LCM will be 140. So this will be minus 7 plus 4. So V comes out to be 140 by minus 3. So that is V for a position of the image of object A. Now let us find the position of the image of object B. For B, U is minus 45 centimeter. Focal length will be minus 20 centimeter. So 1 by V is equals to 1 by F, which is minus 20 minus of minus 45. So the LCM will be 180. So it will be minus 9 plus 4. So this will be minus 5 by 180. Or we can further simplify this. It will be minus 1 by 36. So V comes out to be minus 36. So we have minus 36 and then we have 140 by 3. So this is what? So 140 by 3. So if I multiply and divide this by 3, so we'll get minus 108 by 3. Okay. So if I show the position of the images on the principal axis. So for A, this is the image, right? And this distance is 140 by 3 centimeter. And if I show the position of B, it will be at a distance of 108 by 3. Okay. So the length of the image will be 140 by 3 minus 108 by 3, which comes out to be 32 by 3. And it is given as x by 3 in the question. So x comes out to be 32. So 32 is the answer of this question. Got it? Right. So let us see the next problem type, and it is based on the speed of the image formed by the plane mirror. So here what we have given, let us say there is an object O and it is moving with a speed of 2 centimeters per second towards the mirror, normal to the mirror. Then the image will move in the opposite direction with the same speed, right? So what we can say with respect to the mirror, velocity of the image with respect to the mirror will be equals to, will be opposite to the velocity of the object with respect to the mirror. So from this, if I use relative motion concept, so velocity of the object in ground frame minus velocity of the mirror in ground frame is equals to negative of velocity of the image minus velocity of the mirror in ground frame. So by rearranging, we'll get this relation, which is velocity of the image in ground frame will be 2 times velocity of mirror minus velocity of the object. Now let us see a question. In this question, we have given an object which is moving with a speed of 3 centimeters per second in the right direction. Mirror is going in the right direction with 2 centimeters per second. And we have to find the velocity of the image. So we can use this formula. So velocity of the image will be 2 times the velocity of the mirror minus velocity of the object. So 2 times velocity of the mirror. So I'm taking right direction as positive. So velocity of the mirror will be 2 minus velocity of the object is 3. So that comes out to be 1 centimeter per second. Okay, so do remember this formula. The next problem type is based on the speed of the image formed by the spherical mirror. So here let us see an illustration. So we have given an object which is placed at 40 centimeter from the pole, and the radius of curvature of a concave mirror is 60 centimeter. And we have to find the speed of the image. So what we're going to do, since the position of the object from the pole is changing, we can say the u will not be constant. So we can say the rate of change of u with respect to time will give us the speed of the object, and the rate of change of v with respect to time will give us the speed of the image. Now if we use mirror formula and differentiate that with respect to time, so we'll get minus 1 by v square is equals to dv by dt minus 1 by u square times du by dt. Now from this we'll get this relation. Now in this relation, we can say this is the speed of the image, or I can say velocity of the image, and this will be the velocity of the object. And v square by u square, you can say this is nothing but the square of the magnification. This is square of the magnification. So you should remember this formula, vi is equals to minus m square v naught. Now if you look at this problem, when the object is at a distance 40 centimeter, its image is being formed at 120 centimeter from the pole, right? So if I substitute the value in this formula, so we have to find the velocity of the image. It will be minus, and v is minus 120 and u is minus 40. Square of that and multiply with v naught. V naught is the velocity of the object, which is 2 centimeter. So times 2 cent. If I'm considering right as positive, then 2 centimeter per second. So this comes out to be minus of, this will give us 3. So 9 times 2, so which is minus 18 centimeter per second. Now we are getting a negative answer, which signifies that the image is going in the opposite direction. So if you look at the image, it is moving in the left direction. So that is the image, right? So I hope this concept is clear. So you have to remember this formula, right? Now let us see another case when the object is moving perpendicular to the principal axis. So here there is an object which is at a distance 40 centimeter from the pole, and the radius of curvature of the concave mirror is 60 centimeter. And the speed of the object is 2 centimeter per second. And in this case, what we can say, the height, if this object rises, then we can say the position of the object from the principal axis will act like a extended object. So we can say the height of the image and the height of the object will be will change in this particular case, but the position of the object and the image will not change. So v and u will be constant. So we can say height of the image. So if I rearrange the terms, so we'll get dhi by dt is equals to m times dh naught by dt, where dhi by dt is nothing but the velocity of the image, and dh naught by dt is the velocity of the object. So by using this, we will get the answer. So we can say velocity of the image is equals to minus v by u times velocity of the object. Let us put the value. So when the object is at 40 centimeter, its image is being formed at 120 centimeter from the pole by using the mirror formula. So we can write this as minus of minus 120 divided by minus of 40, because the object is 40 centimeter from the pole and velocity of the object is given as 2 centimeters per second. So by this will give us 3. So it comes out to be minus 6 centimeter per second. Okay, again, you have to remember this. So I have discussed 10 problem types from reflection. Now let us start the next block, which is the 7 problem types in refraction. So I hope your confidence in the problem related to mirror has improved. Right, so now let us start. I am going to discuss these 7 problem types one by one. So the first is based on the speed in a medium, speed of light in a medium. So what you can remember, so there is a term known as the refractive index, and it is nothing but the factor by which the speed of light in a medium reduced, as if we compare the speed of light in vacuum. So mu will be so from this we can say the speed of light in medium will be given by c by mu, where mu is the refractive index, c is the speed of light in vacuum. And speed of light in vacuum is 3 into 10 raised to 8 meters per second. And when light moves from one medium to another, the wavelength changes, but the frequency doesn't change. That you have to remember. Right, so let us see the question based on this concept. So difference of speed of light in two media A and B is 2.6 into 10 raised to 7 meters per second. If the refractive index of the medium B is 1.47, and then the ratio of the refractive index of medium B to medium A. So we have to find mu B upon mu A, and we have given VA minus VB as 2.6 into 10 raised to power 7. So we know that speed is given as speed of light in vacuum divided by the refractive index. So we can write this as C divided by mu A minus C divided by mu B. So that will be 2.6 into 10 raised to power 7. And we have given the refractive index of medium B is 1.47. So mu B is given. So mu b is 1.47. So let us simplify this. So from this, I can just remove this c. Let us take this c on the other side. So it will be 3 into 10 raised to power 8. So which comes out to be 2.6 divided by 30, right? And so 1 by mu a comes out to be 2.6 divided by 30 plus 1 by mu b, which is 1.47, right? And we have to find the ratio. Okay, right. So now what we can do, let us multiply left hand side with the right hand side, right? Left hand side with mu b and right hand side with mu b. And mu b is 1.47. 1.47. So it will be mu b by mu a, and this comes out to be 1.47 times 2.6 divided by 30 plus 1. So we have to find what is this value, right? And we'll get the answer. So if I simplify this, so let me just simplify this. So this will be 10 and it will be nearly 0.9. And from this value comes out to be 94. Yes, so this comes out to be nearly equals to 0.13, right? So 0.13 plus 1. So the answer will be 1.13, right? So option C is the right answer. So the next problem, let us see. The relative permittivity of distilled water is 81. The velocity of the light in it will be, and we have given mu r as 1. Okay, so you should remember that the speed of light in a medium will be given as c divided by refractive index, and this mu can be written as square root of mu r times epsilon r, where mu r is the relative permeability and epsilon r is the relative permittivity. And here we have given mu r as 1. So the refractive index will be root of 1 times 81, which is 9. So we got the refractive index and we have to find the speed. So V will be 3 into 10 raised to power 8 upon 9. So that will be 0.33 times 10 raised to power 8. So 3.33 times 10 raised to power 7. So option 3 is the right answer. Now let us see the next illustration based on the same problem type. So time taken by light to travel in two different materials, A and B, of refractive indices mu A and mu B of same thickness. So we have given two materials. So this is material A and this is material B, and the thickness is same. So let us, this length is x and this length is also x, right? And the time taken by the light in material A is t1 and in material B is t2. And t2 minus t1 is given as 5 into 10 raised to power minus 10 seconds, and the ratio of refractive indices is 1:2. So mu A by mu B. So mu A upon mu B is given as 1/2. Then the thickness of the material in meters, and we have given VA and VB are the velocities of the light in material A and B respectively. Right, so we know that speed of light in a medium is given as C divided by refractive index. Okay, so we can say T2, and time is distance upon speed. So T2 can be written as distance upon VB minus distance upon VA is equals to 5 into 10 raised to power minus 10. So we can say x can be written as so x can be, so we have to find the value of x. So x can be written as 5 times 10 raised to power minus 10 VA VB divided by VA minus VB. Okay, so if you look at the option, we know the ratio of refractive indices, right? So we won't get the numerical answer in that case. So let us find the answer in terms of VA, right? So let us first find the answer in terms of VA and then we'll find the answer in terms of VB. So VB can be written as C divided by mu b. Okay, so x can be written as 5 into 10 raised to power minus 10 VA times C divided by mu b divided by C 1 by mu a minus 1 by mu b. Okay, so this C will get cancelled out. Or I can write this as 5 into 10 raised to power minus 10 times VA divided by mu b by mu a minus 1. So this can be written as 5 into 10 raised to power minus 10 times VA divided by, what is mu b by mu a? That will be 2, na? Mu a by mu b is 1 by 2, so that will be 2. So 2 minus 1. So it comes out to be 5 into 10 raised to power minus 10 VA meters. So if you look at the option A, that is the right answer. Okay, let us see another question. So the red light differs from blue light as they have. So two different colors light in a same medium have different wavelengths and different frequencies. So they will be having different frequencies and different wavelengths. So option 1 is the right answer. Now the next concept, next problem type that we have to discuss is Snell's law. Now what is Snell's law? When the light moves from one medium to another, there will be bending in the light. So if the light moves from a rarer medium to a denser medium, then it will bend towards the normal. In the other way around, it will be away from the normal. And we can apply this relation. So mu1 sine I is equals to mu2 sine R. Okay, so let us see the application of Snell's law. So consider light ray traveling in air is incident into a medium of refractive index root 2 times n. I think it is root 2 times n. So this n is outside. The incident angle is twice that of the refracting angle. So angle of incidence, if this angle is theta, is twice. Right, so this angle is twice. So let me show it like this. So if the angle of refraction is theta, refracting angle is also known as the angle of refraction. So this will be 2 theta. And traveling in air. So air is, okay, right. So this is air and this is medium. And refractive index is given as root 2n. Okay, let me take it as root 2n only, right? Root 2n. So if we apply Snell's law, so sine of 2 theta times 1 is the refractive index of air, is equals to root 2n times sine of theta. So if we simplify this, the left hand side will be 2 sine theta cos theta. So I have used the identity of sine 2 theta is root 2n sine theta. So this sine theta will get eliminated. So cos theta will be nothing but root 2n upon 2, which is root of n by 2. So theta comes out to be cos inverse root of n by 2. So option, let me again check. Then the angle of, okay, so we have to find the angle of incidence. Sorry, not it, angle of incidence. So that is the angle of refraction. So angle of incidence will be twice of that. So 2 times cos inverse root n by 2. Yes, option D is the right answer. That is not the right answer. Let us see the next question. If a wave gets refracted into a denser medium, so this is rarer and this is denser. So ray is getting into the denser medium. Which of the following is true? Wavelength, speed and frequency decreases. Wavelength, speed and frequency. So frequency depends upon the source, right? So frequency will remain same. So option A is incorrect. Wavelength increases, that is incorrect. Wavelength speed decreases, but frequency remains the same, right? So wavelength decreases when the light enters from a rarer medium to a denser medium, and the wavelength in denser medium will be lambda naught, which is in the vacuum, divided by refractive index of the denser medium, right? Right, so option C is the right answer. Let us see the next question. Light enters from air into a given medium at an angle of 45 degree with the interface of air and medium. After refraction, the light gets deviated through an angle of 15 degree from its original direction, the refractive index of the medium. So light, this is air and this is the medium, and light is coming like this, and the angle of incidence is given as 45 degree. So it will bend towards the normal, and let's say this angle is R, and it is getting deviated by 15 degrees. So that was the original direction, and it has rotated by an angle 15 degrees. So we can say 45 and R plus 15 must be equal. They are vertically opposite angles. So 45 is equals to R plus 15. So R will be 30 degrees. Now we know what is the angle of refraction. So we can apply Snell's law. So 1 times sine of 45 should be equals to mu times sine of 30 degrees. So that will be 1 by root 2 divided by sine 30. So that will be 2 by 1. So that will be refractive index. So it comes out to be root 2. So 1.414 is the answer. Now let us see the next illustration based on Snell's law. The xy plane be taken as the boundary between two transparent media M1 and M2, where M1 in Z greater than equals to 0 has a refractive index root 2, and M2 with Z less than 0 has a refractive index root 3. Okay, let me just draw the diagram. So we have xy plane. So this is x, this is y, and this direction will be z. So if I consider, say, a plane which is an xy plane, right? So above this plane, the refractive index is root 2, and below this plane, the refractive index is root 3. Let me show. So here the refractive index is root 2, and below that the refractive index is given as root 3. Now there is a ray which is a ray of light traveling in medium m1. So this red one is m1 along the direction given by the vector 4 root 3 I cap minus 3 root 3 j cap minus 5 k cap. So let us say it is in this particular direction, right? So that is the incident ray. Now we want to find the angle made by this incident ray with the normal, and the normal to this interface will be the positive z direction. So what is the angle between what is the angle of incidence? So we can find the angle between minus k cap and the vector which is along the incident ray. So let us say we can apply this relation. So cos I will be a dot minus k cap divided by product of the magnitudes, right? So let us simplify this. So a dot minus k will be nothing but 5. Can you see? Here we have minus 5 and this is minus 1, so that will be 5. Now what is the magnitude of a vector? So let us find the magnitude of a vector. So this comes out to be root of 16 times 3 plus 9 times 3 plus 25. So which is root of 48 plus 27 plus 25. So 48 plus 27 will be 75. So that comes out to be 10. So 10 times 1, so it comes out to be 1 by 2. So from this we can say the angle of incidence will be 60 degrees. Now we know angle of incidence. Now let us apply Snell's law at the point of incidence. So we can say root 2 times sine 60 is equals to root 3 times sine r, where r is the angle of refraction. So root 2 times root 3 by 2 divided by root 3. So that will be sine r. So root 3 will get cancelled out and it comes out to be 1 by root 2. So it means r is 45 degrees. And we have to find the value of the difference between the angle of incidence in M1 and the angle of refraction. So angle of incidence is 60 degrees and angle of refraction is 45 degrees. So the difference will be 15 degrees, right? So 15 is the answer of this question. Right. So let us see the next question. A monochromatic light wave which is having a wavelength lambda 1 and frequency nu 1 in air enters another medium. If the angle of incidence and the angle of refraction are 45 and 30 degrees, then the wavelength lambda 2 and the frequency nu 2 of the refracted wave. So whenever light enters from one medium to another medium, frequency doesn't change because frequency depends only on the source. So frequency will remain same. So nu 2 will be equals to nu 1. So option 1 and option 3 are incorrect. Now we have to find the wavelength. So wavelength changes when we go from one medium to another. So we can say mu 1 sine 45 is equals to mu 2 sine 30 by applying Snell's law. And mu 1 can be written as c divided by the velocity. And velocity can be written as frequency times the wavelength. So times 1 by root 2, and mu 2 can be written as c divided by frequency times the wavelength, and sine 30 is 1 by 2. So from this, frequency will get cancelled out, c will get cancelled out, and we have to find lambda 2. So lambda 2 will be lambda 1 by root 2. So option 2 is the right answer. Now let us see the next illustration. So here we have given a pole is vertically submerged in a swimming pool such that it gives a height, it gives the length of the shadow as 2.15 meters within the water when the surface is, when the sunlight is incident at an angle of 30 degrees with the surface of water. If the swimming pool is filled up to the height of 1.5 meter, then the height of the pole above the water surface in centimeters. Right, so first let us draw the diagram. So here we have given, let's say this is the free surface. And this is the swimming pool bed. And this is the pole. And the height, water is filled up to the height of 1.5 meters. And if we consider sun rays makes an angle of 30 degrees with the horizontal. So that is the sun. So rays are coming like this. So this angle is 30 degrees. So we can see the angle made, so the angle of incidence on the interface will be 60 degrees. So the rays will bend towards the normal. So that will be the image of the tip of the pole. So this will be the length of the shadow. And length of the shadow is given as 2.15. Right? And we have to find the portion of the pole which is outside the pool. So let us call this height as x. Right? So what we can do now, we need to find x. So to find x, we require this length. Let me call this length as y. So if you know y, we'll be able to find x. So in order to find y, we need, what is this? Length z. Okay. So once we know z, we can find y, and if you know y, we can find x. Okay, so what is this angle? Let me call this angle as r. So if you apply Snell's law at the point of incidence, so sine 60 degrees will be equals to refractive index of water, which is given as 4 by 3 times sine r. Now from this, 3 root 3 by 8 will be sine r. Okay, now if you consider this triangle, in this triangle, if we apply tan r, we'll get the value of z. So z divided by 1.5. Okay, so from this, tan r can be written as 3 root 3 divided by root 8 square minus 3 root 3 square. So that should be equals to z by 1.5. Now from this, it will be 4.5 times root 3 divided by root 64 minus 27. Right, so that comes out to be 37, right? So 4.5 root 3 divided by root 37. Okay, so this will be the value of z. So if we simplify this, let me find the exact value. So 4.5 times root 3 divided by root 37. So it comes out to be 1.28 meters, right? So we got the value of z. So y will be 2.15 minus 1.28. So it comes out to be 0.87. Right, so now in this right angle triangle, if we consider this right angle triangle, tan 30 will be equals to x by y is 0.87, and tan 30 is 1 by root 3 times 0.87 will be x. So 0.87 divided by root 3, so that will give us around 0.50 meters, and we have to find the answer in centimeters. So multiply this with 100, so it comes out to be 50 centimeters. So 50 is the answer of this question. Okay, so only the calculation is tricky in this question, rest of the question is easy. So the next concept is based on the apparent shift and apparent depth concept. So if suppose if we are given an object which is placed in a medium, let us say mu r, and d is the original depth of the object from the interface. So that is the interface and this is the observer. And to this observer, the image is being formed at a distance dA from the interface. Now this dA is known as the apparent depth, and it can be given as d divided by mu r by mu d, where mu r is the refractive index of the object and mu d is the refractive index of the observer. Okay, so this formula you can remember. Now, what is apparent shift? If you look at the distance between the object and the image, now this distance is known as the apparent shift. So apparent shift is nothing but the difference of dA and d. Okay, so let us see the apparent shift reduced by a thin slab. Suppose there is a slab of thickness t and a refractive index mu. Now in this case, the apparent shift will be given as t times 1 minus mu naught by mu, where mu naught is the refractive index of the observer and mu is the refractive index of the slab and t is the thickness. So just remember this relation, right? Okay, now let us see a question. An ice cube has a bubble inside. When viewed from one side of the apparent distance of the bubble is 12 centimeter. So I have given a cube, ice cube, and there is a bubble inside. It can be anywhere. Let us say it is here. Now if you are looking at it from the right side, the apparent depth is given as 12 centimeter. So 12 centimeter is the apparent depth. Now when viewed from the other side, now if you are viewing this from the other side, the apparent distance of the bubble is observed to be 4 centimeter. So this distance is 4 centimeter. If the side of the ice cube is 24, so this side is given as 24 centimeter, and let us say this bubble is somewhere here. So that is the bubble. And we have to find the refractive index. Let us say mu is the refractive index. Now if we consider incident rays going in the left direction, right? So when we are viewing this from the left side, we can say the apparent depth is 12 and the formula is original depth. Let us say the original depth is x1. x1 divided by the refractive index of the object, which is mu, by refractive index of the observer, which is 1. So from this, x1 will be 12 times mu. Similarly, if we consider rays going in the right direction, now for this observer, apparent depth is given as 4 So that will be original depth. Let me call this as x2 divided by refractive index of the object upon refractive index of the observer. So x2 comes out to be 4 times mu. Now we know x1 plus x2 is nothing but the edge of the cube, which is given as 24, and it is nothing but 12 mu plus 4 mu. Now from this, 24 divided by 16 will give us refractive index. So this will be 3 by 2 or 1.5. So option 2 is the right answer. Let us another question. As shown in the figure, a plane mirror is fixed at the height of 50 centimeter from the bottom of the tank containing water, which is having a refractive index of 4 by 3. The height of water in the tank is 8 centimeter, and the mirror is placed at a distance of 50 centimeter from the bottom. A small bulb is placed at the bottom of the water tank. The distance of the image of the bulb formed by mirror from the bottom of the tank. So we have to find the distance of the image formed of the bulb formed by the mirror from the bottom of the tank. So let us see. Let us first draw the ray diagram. So I'm considering a ray which is exiting the water normally, and there is another ray which is oblique. So this ray will bend away from the normal. So we can say the first that will be the image. Let me call this as I1, and this is the object. So I1 is the image of the object O because of the refraction, right? So light is going from a denser medium to a rarer medium. So we can say if this is the original depth, so 8 is the original depth. So the apparent depth will be original depth divided by refractive index of the object, which is in this case will be 4 by 3 divided by the refractive index of the observer. Observer is outside, so it will be 1. So this can be written as 8 times 3 by 4, or you can say it will be 6 centimeter. Now I1 is at a distance of 6 centimeter from the interface. Now due to the mirror, the image of I1 will be formed at a distance of, okay, right. So let me just find this distance. So this distance will be 50 minus 8, that will be 42. Now the I1 is at a distance of 42 plus 6, that will be 48 centimeter from the mirror. So its image will be formed at a distance of 48 centimeter behind the mirror. Somewhere here, let us say this is I2, and this distance is 42 plus 6, which is 48 centimeter. And we have to find the distance of I2 from the bottom of the tank. So this distance will be 48 plus 50, 48 plus 50, right? Which comes out to be 98 centimeters. So 98 is the answer of this question. Let us say this question. Two immiscible liquids of refractive indices 8 by 5 and 3 by 2 are put in beaker as shown in the figure. The height of each column is 6 centimeter. A coin is placed at the bottom of the beaker for near normal vision. The apparent depth of the coin is, so we have to find the apparent depth from the free surface. So the observer is placed outside. So let us first find the apparent shift. So we can consider these two immiscible liquids as two slabs which are joined together, and we know the shift produced by the slab will be 1 minus mu naught by mu, where mu naught is the refractive index of the observer and mu is the refractive index of the slab. Now you simply have to add up the shifts by both the slabs. So apparent shift will be 6, 6 is the thickness, 6 times 1 minus 1 divided by mu, that will be 8 by 5, plus 6 times 1 plus, sorry, minus 1 by 3 by 2. Okay, so this comes out to be 6 times 3 by 8 plus 6 times 1 by 3. So this will be 3, this will be 4, and this will be 2. So it comes out to be 9 plus 8 by 4. So that will be 17 by 4. So that is the apparent shift. And we want to find the apparent depth. So let us say the shift due to that, the shift produced is 17 by 4 centimeter, and we want to find the apparent depth. Let us say apparent depth is x. So x plus 17 by 4 is 6 plus 6. So x will be 12 minus 17 by 4, which is 16 or 48 minus 17 by 4. And x is given as alpha by 4. So alpha by 4. So alpha comes out to be 31. Right? Now the next problem type is based on glass slab. And this is the glass slab of thickness t, and the incident ray makes an angle of and the angle of incidence is I. And in this case, in case of a glass slab, the incident ray and the emergent ray, they will be parallel to each other. So angle of incidence will be equals to angle of emergence. And the lateral shift is the perpendicular distance between the incident ray and the emergent ray. So that is the emergent ray, right? And the lateral shift is given by t times sine I minus r upon cos r, where I is the angle of incidence, r is the angle of refraction, t is the thickness, right? So this formula you should remember. Let us see a question. A light ray is incident on a glass slab of thickness 4 root 3 centimeters. So that is t. Refractive index, this is mu. The angle of incidence is equals to the critical angle of the glass slab. So critical angle is defined as sine inverse 1 by mu, and mu is root 2. So that will be sine inverse 1 by root 2. So it means critical angle is 45 degrees. So if critical angle is 45 and we have given angle of incidence is equals to the critical angle, so this is also the angle of incidence. The lateral displacement of the ray after passing through the glass slab. So what is the formula of lateral displacement? So d is t times sine I minus r divided by cos r, right? Now if you apply Snell's law, if this is the glass slab, angle of incidence is given as 45 degrees and angle of refraction is r. So sine 45 is equals to root 2 times sine r. So it will be 1 by 2 equals to sine r. So r comes out to be 30 degrees. So sine, so r is 30, I is 45. So let us simplify this. So d will be, so from this, d comes out to be, thickness is 4 root 3 centimeter, and sine I minus r, that will be 45 minus 30. So we can say sine 45 cos 30 minus cos 45 sine 30 divided by cos r, and it will be cos 30. So let us simplify this. So 4 root 3 1 by root 2 minus 1 by root 2 times tan 30, which will be 1 by root 3. So this comes out to be 4 root 3 by root 2 times root 3 minus 1 divided by root 3. But if you look at the question, they have given sine 15 value, take it as 0.25. So what we can do, we can directly plug in the value of I minus r. I minus r is nothing but 15 degrees. So we can also find the value of d by using the given data. So it will be 4 root 3 times 0.25 divided by cos 30, which is root 3 by 2. So this will get cancelled out and it will be nothing but 2 centimeters, right? So the next concept or the next problem type is based on TIR, that is total internal reflection. And what is the condition for TIR? First of all, the object should be placed in a denser medium. The ray should move from the denser medium to the rarer medium. So that is the first condition. And the angle of incidence on the interface should be greater than the critical angle. And what is the critical angle? It is given by sine inverse mu r by mu t, where mu r is the refractive index of a rarer medium and mu t is the refractive index of the denser medium. And suppose if we have given two media 1.2 and 1.1, then the critical angle will be sine inverse 1.1 by 1.2. And R is known as the radius of the circle of illuminance. So the light which is coming out from denser medium to the rarer medium, it lies only in this region, right? So if the light is incident on the periphery of this circle, then the refracted light will grazes the interface. So we can say light is coming out from the denser medium to the rarer medium only through this circle. Now this is known as circle of illuminance, and R will be given as h upon root mu d by mu r square minus 1. So this you have to remember. So let us see a question. So here a ray of light passes from a denser medium to a rarer medium at an angle of incidence I, and the reflected and the refracted rays makes an angle of 90 degrees with each other. Right? The angle of reflection and refraction are respectively r and r prime. The critical angle is given by. Right. So we know that critical angle is sine inverse refractive index of a rarer medium upon refractive index of the denser medium. Now in this case, a ray of light is going from a denser to a rarer, so this will be the critical angle. So let us say this is mu d and this is mu r, and this angle is I, and we have given the angle between the reflected and the refracted ray is 90 degrees, so this angle is 90. So this r prime is nothing but 90 minus r, right? So if we apply Snell's law at the point of incidence, so sine I times mu d is equals to mu r times sine r prime. So which can be written as sine I divided by cos I equals to mu r upon mu d, and this is nothing but sine c. Okay, so it will be tan I equals to sine c. So we can say the critical angle will be sine inverse tan I. Sine inverse tan I. So I is nothing but r, right? So it will be option 4, right? Fourth option is the right answer. Let us see next question. The critical angle for a denser rarer interface is 45 degrees. The speed of light in the rarer medium is 3 into 10 raised per 8. The speed of light in the denser medium is. So we know that sine of a critical angle will be mu r by mu d, and here the rarer medium is air, so that will be 1, and mu d is mu. The speed of light in the denser medium we have to calculate. So from this sine 45, critical angle is given as 45, so it will be 1 by root 2, so mu comes out to be root 2. So the speed of light in the medium, in a denser medium, will be speed of light in vacuum divided by the refractive index. So it is 3 divided by root 2 times 10 raised per 8, which comes out to be around 2.12 into 10 raised per 8 meters per second. So option 2 is the right answer. Let us see the next question. Critical angle of incidence for a pair of optical media is 45 degree. The refractive indices of first and the second media are in ratio. So this question is similar to the last question. So I'm just keeping this question as a homework for you. So the answer will be option 2. Now let us see the next problem type, and it is based on the refraction at a spherical interface. So here we have given on the convex side there is a refractive index n1, on the concave side there is a refractive index n2, and there is an object which is placed at a distance u from the center of this interface, and v is the position of the image, and the center of curvature or the radius of curvature is r, and c is the center of curvature. Now in this case n2 by v minus n1 by u is given as n2 minus n1 divided by r. So that is the formula that you have to remember, and whenever you have to apply this formula, always use proper sign convention. For example, if the incident rays are going in the right direction, all distances measured in the direction of incident rays are taken as positive, and against the incident ray are taken as negative. Now let us see the question based on this concept. The image of an object placed in air formed by a convex refracting surface is at a distance of 10 meters behind the surface. So convex, so we have given a convex reflecting surface and its image is being formed behind the mirror at a distance 10 meter. So that is the image. The image is real and is at 2/3 of the distance of the object from the surface. And it is 2/3 of the distance of the object from the surface. So if this is the object and this distance is x, then this distance of the image 10 is 2/3 of x. So that is given. The wavelength of the light inside the surface is 2 by 3 times the wavelength of light in air. So lambda in medium is given as lambda naught by mu, which is nothing but 2/3 of the wavelength in air. Now from this we can say the refractive index is nothing but 3 by 2. Now we know the refractive index, so we can find the speed. So we got the refractive index in this region, which is 3 by 2. And here we have air. The radius of curvature, a curved surface, is x by 13. So r is given as x by 13 meters and we have to find the value of x. Okay, right. So let me take this as some other variable. Let us take this x as y. I'm taking this as y. So from this y comes out to be 15 meters. Now we can apply the formula. So it is mu2 by v minus mu1 by u is equals to mu2 minus mu1 by r. Now in this case, mu2 is the refractive index of the medium of refraction. So rays going from air to the medium, which is 3 by 2, refractive index is 3 by 2. So mu2 is 3 by 2 and v is given as 10 minus mu1 is 1 and u will be minus 15. And mu2 minus mu1 will be 3 by 2 minus 1 and the radius of curvature is, let us take it as r and we have to find r, right? So let us simplify this. So this comes out to be 3 by 20 plus 1 by 15 times 1 times 2 by 1. So that will be 1 by r. So this can be written as LCM will be 60. So 60 times 9, 60 and this will be 9 plus 4 times 2 is 1 by r. So from this 30 by 13 is the radius of curvature and it is given as x by 13. So x will be 30. Okay. So 30 is the answer of this question. Now let us see one more question. Region 1 and 2 are separated by a spherical surface of radius 25 centimeter. An object is kept in the region 1 at a distance 40 centimeter from the surface. So this is the radius of curvature r and this is the position of the object. So this is u. So u is minus 40. Radius of curvature is minus 25 centimeter. And the distance of the image. So we have to find v. So let us apply the formula. So mu2 by v minus mu1 by u is equals to mu2 minus mu1 by r. So mu2 in this case is the refractive index of the medium of refraction. So in this case it is 1.4. So 1.4 divided by v minus and medium of incidence is 1.25. So 1.25 divided by u and u is minus 40. So 1.4 minus 1.25 divided by r and r is given as minus 25. Now from this we can say 1.4 by v is equals to plus and this can be written as 5 by 4. So 5 by 160 and this will be 0.15 upon minus 25. So this can be written as 0.03 divided by minus 5 or we can write this as 3 by 500. This can be written as 1.4 by V, and it will be minus, so this should be negative, no? So minus 3 by 500 minus 5 by 160. So let us simplify this. So it comes out to be 32. So minus 96 minus 500 divided by 161,600, and that will be 1.4 by V. So V upon 1.4 will be 1600 times 14 divided by minus 596. Okay, I have taken this on the other side, right? V will be 1600 times 14 upon minus 596. So 1600 times 14 divided by 596. So it comes out to be nearly equals to 37.58 with a negative sign. So option 4 is the right answer. So we are done with the problem type associated with refraction. Now let us see the different problem types which can be formed for prism topic. So here these are the 6 problem type. Let me discuss these problem one by one. So the first concept is the first problem type is based on the minimum deviation condition. And what do we mean by that? So first of all, you should know that the angle of refraction R1 and this angle of incidence R2 on the second interface, the sum of these two angles is equals to the angle of prism, if this is A, right? And the deviation is given as I plus E minus A, right? So these are the two important formulas. And for minimum deviation, what happens? The angle of incidence, which is I1, is equals to I2. So in this condition, I1 is equals to I2, or you can say I will be equals to E. And when that happens, the minimum deviation will be given as 2 times I minus I, right? So I can be written as A plus minimum deviation divided by 2. And the refractive index for a prism is given by sine of A plus del min by 2 divided by sine A by 2. Okay, so this formula you should remember. And at minimum deviation, the refracted ray will be parallel to the base. Okay, so that is the condition. And when that happens, when I1 is equals to I2, then R1 is also equals to R2. R1 is also equals to R2, and both equals to A by 2. Okay, so this you should remember. That is for minimum deviation condition. Now let us see the question based on this. If the refractive index of a material of a prism is cot A by 2, where A is the angle of the prism, then the angle of minimum deviation. So refractive index is given as cot A by 2. And we know that refractive index is sine A plus minimum deviation divided by 2 upon sine A by 2. So this can be written as cos A by 2 upon sine A by 2. So let us eliminate sine. So from this we can say sine A plus del min by 2 will be equals to, and cos A by 2 can be written as sine of pi by 2 minus A by 2. So if we compare left hand side with the right hand side, it will be A by 2 plus del min by 2 equals to pi by 2 minus A by 2. So let us remove this 2. So del min will be pi minus 2A. So option 1 is the right answer. Let us see the next question. The refractive index of a prism is root 3, and the ratio of the angle of minimum deviation to the angle of prism. So we have to find del minimum divided by A. So that's what we have to calculate. Okay, this is given, sorry. This is given as 1, and we have to find angle of prism. So we have to find A value. So refractive index is given. So we know root 3 will be sine A plus del min by 2 divided by sine A by 2. Okay. And the ratio is given. So we can write del min as A. So this can be written as sine A plus A by 2 divided by sine A by 2. So this will be sine A upon sine A by 2. Okay, right? So now what we can write? Sine A can be written as 2 sine A by 2 times cos A by 2 divided by sine A by 2. So let us eliminate sine and sine A by 2, right? So root 3 by 2 comes out to be cos A by 2. And we know that cos 30 degrees, or cos pi by 6 will be root 3 by 2. So from, if we compare this, then A by 2 comes out to be pi by 6. So A will be pi by 3. So which comes out to be 60 degrees. So 60 is the answer of this question. Right. So let us see another question. The refractive index of the transparent liquid filled in a equilateral hollow prism is root 2. The angle of minimum deviation for the liquid will be. So we have to find minimum deviation. And it's an equilateral hollow prism. So equilateral, right? So A will be 60 degrees. So we can say root 2 will be equals to sine 60 plus minimum deviation by 2 upon sine A by 2. That will be 60 by 2. And sine 30 is root 3 by 2. Oh, sorry, 1 by 2. So that will be root 2 by 2 equals to sine 30 plus minimum deviation by 2. So this can be written as sine pi by 4. Clear? Because root 2 by 2 is nothing but 1 by root 2. So from this will be 45. So 30 degrees plus minimum deviation by 2 will be 45 degrees. So the minimum deviation will be 30 degrees. Okay, so 30 is the answer of this question. Now the next problem type is the graph between deviation versus the angle of incidence in case of a prism. Now if you look at this graph, there will be an angle of incidence at which the deviation will be minimum, right? Clear? So as we increase the angle of incidence, what happens? The deviation first decreases and then it increases. And if you consider 2 points on the graph which is having same angle of deviation, and we know the angle of deviation is I plus A minus A, right? So these 2 points have same angle of deviation. Suppose at this particular point, the angle of incidence is I and angle of emergence is E. Then at this particular value, the angle of incidence will be E and the angle of emergence will be I. Is it clear? Because I plus E, the sum of I plus E should be same for same deviation because A is not changing. So that you have to remember, right? Now let us see the question based on this. The expected graph represented of the variation of the angle of deviation with the angle of incidence. Yes, we have just seen it will be option number 2. And it is not a parabola, do remember that. The next problem type is based on the dispersion of light, of white light with the prism. So if you look at this diagram, the white light, it splits up into different parts. And if you consider the violet color bends the most and the red color bends the least. Why this difference is there? Because the wavelength, or you can say the refractive index of the prism depends upon the wavelength of light. So in case of the red light, the wavelength is maximum. You can say it, wavelength of lambda will be greater than the wavelength of violet light. So the refractive index for this prism will be less for the red light. So you can remember this formula. Refractive index is given as some constant plus some constant by lambda square. So if you increase lambda, refractive index will decrease. So lambda of red is greater than lambda of violet. That's why the refractive index of this prism with respect to red light will be less than the refractive index of this prism with respect to violet light. Now there are some more terms which you have to remember if you are talking about dispersion. So first is the angle of dispersion, right? So what is this? So it is the It is this angle. If I show that, if this is visible, hmm, this angle, right? What is this angle? It is the angle between the emergent red light and the emergent violet light. So this can be written as del V by del R, where del V is the deviation produced in the violet light and del R is the deviation produced in the red light. Now here you have to remember one thing, that for thin prism, the deviation can be given as A times mu minus 1, and in case of a violet light, this can be written as A times mu V minus 1, where mu V is the refractive index of this prism with respect to the violet light. And del R, or the deviation produced in the red light, will be A times mu R minus 1, where mu R is the refractive index of this prism with respect to red light. Now if you take the difference of these two deviation, we'll get the angular dispersion, which is A times mu V minus mu R. Now another important physical quantity is mean deviation, and it is the deviation produced in the yellow light. So we can write this as mu y minus 1 times A. So these formulas are applicable for thin prism, right? So whatever formulas that we are looking at. Then the third important physical quantity is dispersive power of the prism, which is denoted with omega, and it is nothing but the ratio of angular dispersion and the mean deviation. And for thin prism, it can be written as mu v minus mu r upon mu y minus 1. And suppose in a question, mu y is not given. It is not given, right? But mu r and mu v are given. So mu y you can take as the mean of mu r and mu v. So that can be taken as mu y. Okay, now let us see some of the questions based on this concept. So when a white light passes through the prism, the red light bends lesser than the yellow and the violet light. So that is correct. So option statement 1 is correct. The refractive indices are different for different wavelengths in dispersive medium, and in the light of the above statement, choose the correct answer for the option. So both the statements are correct, right? So option 3 is the right answer. Now let us see another problem type, and it is based on the achromatic combination of the prism. So what is achromatic? In this case, when we connect two prisms in the reverse order, we'll get a white light as the emergent beam, right? So in this case, we can say there will be no dispersion. There will be deviation, but no dispersion, right? No dispersion, but deviation. Or you can say deviation without dispersion. So in this case, the angular dispersion, so net angular dispersion will be theta 1 minus theta 2, which will be 0. Okay, so we can write this as mu v1 minus mu r1 times a1, or let us say a, minus mu v2 minus mu r2 times a prime should be 0. And what should be the mean deviation? So mean deviation will be given as del y1 minus del y2. So that is the deviation produced by the first prism. This is the deviation produced by the second prism, and we are taking the difference. Why we are taking the difference? Because two prisms are connected in reverse order, and this will be mu y1 minus 1 times a minus mu y2 minus 1 times a prime. Okay, so this you have to remember. This is the net deviation, and that is the condition, right, for deviation without dispersion. Now let us see the question based on this concept. A deviation of 2 degree is produced in a yellow ray when a prism of crown and the flint glass are achromatically combined. So the net deviation is given, that is 2 degrees, and that will be mu y1 minus 1 times a minus mu y2 minus 1 times a prime. Taking dispersive power of crown and flint glass are 0.02 and 0.03 respectively, and refractive index for the yellow light as for these glasses is 1.5 and 1.6. So mu y1 is given as 1.5 and mu y2 is given as 1.6. We have to find the refracting angles for the crown glass prism will be, so we have to find A1, right? We have to find value of A. Okay, so what we have given, so this is given, A prime is also not given to us, right? So let us substitute the value. So 2 will be 1.5 minus 1 times A minus 1.6 minus 1 times A prime. So we got this relation. And the another relation we will get by using the concept of dispersive power. So it is given as 0.02 and 0.03. So what is dispersive power? So theta, and it's a achromatic combination. Na? So we can say theta 1 will be equals to theta 2. And we know that theta can also be written as dispersive power times the mean deviation. So this can be written as omega 1 del y1 is equals to omega 2 del y2. What is omega 1? That is given as 0.02, and del y1 will be 1.5 minus 1 times A, and omega 2 is 0.03, and this can del y2 will be 1.6 minus 1 times A prime. Now from this equation we'll got the ratio of A and A prime. Now we got two equations. So this will give us 2 equals to 0.5A minus 0.6A prime, or we can write this as 5A minus 6A prime is equals to 20. So that is first equation. Now from this we can remove this decimal, and this comes out to be 0.5 times 2, so this will be A, and it will be 0.6 times 3, it will be 1.8. So A is 1.8 times A prime, and we have to find the value of A. Okay, first let us find the value of A prime. So let me use these two equations. Now we have pair of linear equations in two variable. So if this equation is 1 and this equation is 2, then we can say A. So 5 times A will be 9A prime minus 6A prime is equals to 20. So 3A prime comes out to be 20. So A prime is 20 by 3. So A will be 1.8 times 20 by 3. So this will be 0.6. So it comes out to be 12. So what we can say, the angle of prism for crown glass will be 12 degrees. The next problem type is based on direct vision prism combination, and it is also known as dispersion without deviation, right? Dispersion without deviation. And what do we mean by that? There is no deviation, so we can say del y1 will be equals to del y2, or you can say mu y1 minus 1 times A is equals to mu y2 minus 1 times A prime, and there will be some net deviation, there will be some net angular dispersion. So theta net will be theta 1 minus theta 2. So that will be mu v1 minus mu r1 times A minus mu v2 minus mu r2 times A prime. So these two formulas you have to remember. That is the condition for direct vision prism combination, and this is the net angular dispersion produced by this combination. So let us see a question. So we have given a thin prism P which is having an angle 6 degrees made of a glass of refractive index 1.54. If a single refractive index value is given, that value is corresponding to the yellow light, is combined with another prism P2 made of a glass of refractive index 1.72 to produce dispersion without average deviation. So there is no deviation. So what we can say, mu y1 minus 1 times A should be equals to mu y2 minus 1 times A prime. So 6 degrees is A, and mu y1 is 1.54. So 1.54 minus 1 times 6 degrees is equals to 1.72 minus 1 times A prime. So this comes out to be 0.54 times 6 divided by 0.72. So we can remove this decimal. So this comes out to be 8, and this will be 7. No, sorry. So this comes out to be 12 and this comes out to be 9. So this will be 4 and this will be 3, 2 and this will be 3. So it will be 4.5. So option 4 is the right answer. The next problem type is based on the case when the incident ray is hitting normally on the first refracting phase of the prism. So in the figure, the face AC of the equilateral prism is immersed in a liquid of refractive index n for incident angle of 60 degrees. At the side AC, the refracted light beam just grazes along the face AC. The refractive index of the liquid is root x by 4, the value of x is. Right, so we have given angle of incidence and here it is grazing the interface. Clear? So it is hitting normally, so it will cross the interface AB undeviated. So if we apply Snell's law at this point of incidence, at a let me call this point as P. So we can say sine 60 times 1.5, which is the refractive index of the prism, is equals to n, and n is root x by 4 times sine 90 degree. Now from this, it will be root 3 by 2 times 1.5 times 4, and sine 90 is 1. So that will be root x. So this will give us 3 root 3, or we can write this as root of 27. So x comes out to be 27. Now we are done with the problem type associated with prism. Now let us see the different problem type that can be formed for lenses. So I'm going to discuss 8 problem types and I'll discuss these problem type one by one. So let us see the very first problem type, and it is based on lens maker's formula. So what is lens maker's formula? With the help of this formula, we can find the focal length uh, of any type of a thin lens. So if the radius of curvatures are given to us, R1 and R2 are the radius of curvatures of both the surfaces, and mu21 is the refractive index of the medium of lens with respect to the medium of the surrounding. So for example, if we have given a lens like this surface has a radius of curvature R1, this surface has a radius of curvature R2, and this lens has a material of refractive index mu2, surrounding material is mu1. Then mu21 can be written as mu2 by mu1, right? So this you can remember. Now for a converging lens, focal length will be positive. So in order to keep focal length positive, then this factor A and B both should be positive or both should be negative, right? And for diverging lenses, focal length has to be negative. So when do we have focal length to be negative? When A is positive and B is negative, and when A is negative, B is positive. So what is the condition for A to be positive? A will be positive if the lens is placed in a rarer medium, if mu2 is more than mu1. And when do we have like condition for A is negative? When mu2 is less than mu1, right? And when do we have B as positive? So B will be positive in case of a convex lenses and B will be negative in case of a concave lenses. Okay, so this thing you have to remember. Now let us the questions based on the same concept. A convex lens of refractive index 1.5, focal length 1.8, 18 centimeter in air is immersed in water. So we have given there is a lens, convex lens. If we have air and it is having a refractive index 1.5, so the focal length is 18 centimeter. Now now we have immersed this lens in water, right? Now it is immersed in water where outside refractive index is 4 by 3 and the lens material has a refractive index 3 by 2. So the new focal length is f1 by f2. Let us say f2 is the new focal length. So that we can write this as mu2 by mu1. Mu2 in this case will be 3 by 2. Mu1 is 4 by 3 minus 1 times 1 by r1, and it's a convex lens, right? So 1 by r1 Okay, right. So if I consider right direction as the direction of incident ray, R1 will be positive and R2 will be negative. So this will become 1 by R1 plus R1 by R2. So 1 by, uh, and I'm assuming that it's a equiconvex lens, or you just write this as 1 by R1 minus 1 by R2. Okay. So we can find the value of 1 by R1 minus 1 by R2 from this focal length. How we can do that? So 1 by 18 is equals to 3 by 2 by 1 minus 1 will be 1 by R1 minus 1 by R2. So now let us eliminate 1 by R1 minus 1 by R2 from these two equations. So this is 1 and this is 2. So if I divide 2 with 1, we will get F2 by 18 equals to 3 by 2 minus 1 divided by 3 by 2 upon 4 by 3 minus 1. So let us simplify this. So 1 by 2 divided by 9 by 8 minus 1. So that will be 1 by 2 times 8 by 1. So that will be 4. So F2 comes out to be 18 times 4. So that comes out to be 76 centimeter, and we have to find the change in the focal length. So 76 minus 18, so that will be 50, 70, sorry, it is 72. 72 minus 18, so that will be 54 centimeter. So 54 is the answer of this question. Right, so let us see next question. A biconvex lens of refractive index 1.5 has a focal length of 20 centimeter in air. If its focal length when immersed in a liquid of refractive index 1.6. So it's a biconvex. So what is a biconvex lens? In which both the radius of curvatures are equal. So I'm assuming equiconvex lens. This is R1, this is R2, and R1 is equals to R2. So focal length is given as 20 in air. So 1 by 20 is equals to 1.5 minus 1. And since both have the same radius of curvature, this will become 2 by R. Now from this we can find the radius of curvature. So this will be 0.5 times 2. So R comes out to be 20 centimeter. So we got R. Now let us again apply lens maker's formula when the lens is immersed in liquid of refractive index 1.6. So 1 by F will be 1.5 divided by 1.6 minus 1 times 2 by R, which is 20. So this comes out to be minus 1 by 16 times 1 by 10. So 1 by F, so focal length comes out to be minus 160 centimeter. So option 2 is the right answer. Now let us see another illustration. The thickness at the center of a plano-convex lens is 3 millimeter and the diameter is 6 centimeter. So this diameter is nothing but the aperture of the lens. If the speed of light in the material of the lens is 2.82 into 10 raised per 8 meters per second, the focal length of the lens. Okay, let us see. First, let us draw the diagram. So we have given a plano convex lens. And this thickness is given as 3 millimeter. And if I draw the center of curvature, this will be the center of curvature and this is the radius. So this will be, let us say R is the radius of curvature. So this will be R minus 3, where R is in millimeters, and half of the aperture will be 3 centimeter or 30 millimeter. So this length will be 30 millimeter. Now, if we want to apply lens maker's formula, we should know what is the radius of curvature. Now we can find the value of R from this right angle triangle by using Pythagorean theorem. So we can say R minus 3 square plus 30 square is equals to R square. So if I simplify this, so R square minus 6R plus 9 plus 900 is equals to r square. So r square will get cancelled out, right? So 6 times r will be 909. So r comes out to be 303 by 2. So that will be 151.5 centimeter. So we got the value of r. And if you look at the options, options are quite far apart, right? So 30, 15, 1.5, 0.3. So we can assume radius of curvature is nearly equals to 150 centimeter. Now let us apply Lensmaker's formula. So 1 by f is equals to, okay, right. So before applying that, we should know what is the refractive index of the lens. Speed is given. So we can say 2 into 10 raised to power 8 is equals to 3 into 10 raised to power 8 divided by the refractive index. So mu comes out to be 1.5. Now we can apply Lensmaker's formula. So 1 by f is equals to 1.5 minus 1, and it's a plano-convex, so it will be 1 by r, and r in this case is 150, approximately 150. So f comes out to be 300 millimeters or 30 centimeters. So option 4 is the right answer. The next problem type is based on the image formation by the lenses. So first we'll see the image formation by the converging lens and then by the diverging lens. So in case of a converging lens, if the object is placed at infinity, then the image will be formed at the focus, and it will be highly diminished image, and it will be real and inverted, right? So this is the first case, right? Now if the object is placed beyond 2f, in that case the image will be formed between f and 2f, right? And it will be diminished, and it will be real and inverted. Now if the object is placed at the center of, or at 2f, the image will be formed at 2f only, this one, right? And it will be of the same size, and it will be real and inverted. Now if the object is placed between 2f and f, the image will be formed beyond 2f, and it will be enlarged, and it will be real and inverted. Now if the object is placed at the focus, the image will be formed at infinity. It is highly magnified image, and it will be real and inverted. But if the object is placed between the focus and the optical center of the lens, in that case the image will be virtual and erect, and it will be on the same side as the object, and it will be enlarged, right? So that you have to remember, and it will be, yeah. And if we consider diverging lens, if the object is placed at infinity, so we're going to consider two cases. If it is at infinity, the image will be formed at the focus. It will be highly diminished, and it will be virtual and erect. But if the object is placed beyond optical center, right, somewhere to the left at a finite distance, then the image will be formed between the optical center and the focus, and it will be virtual and erect and diminished image. So that you have to remember. Now let us see the question based on this concept. And apart from this, just also remember the lens formula. So 1 by v minus 1 by u is equals to 1 by f, and the magnification will be given as v by u. Okay. So now let us see the illustration based on this problem. So here we have given the same size images are being formed by the convex lens when the object is placed at 20 centimeter or at 10 centimeter from the lens, the focal length of the convex lens, right? So we have given two different positions. Let us say this is u1 and this is u2, and we are getting the same size of the image. Now let us see when this can happen. So convex lens is there. So if you consider, say, the object which is placed between the focus and the optical center, in that case we'll get a virtual and erect image, magnified image. But suppose if we consider a case where object is placed between 2f and f, so in this case also we'll get a magnified image, but this will be a real and inverted image. So here, if the distance is less, we can say we'll get the case of a virtual and erect image. So if this height is h naught, so this is also h naught, right? And this distance will be nothing but 10 centimeter, and this distance will be 20 centimeter. So let me take, so u1 will be minus 20 and u2 will be minus So yes, u2 will be minus 10 centimeter. And the size of the image is same, so we can say the magnification will be having the same magnitude. But if you look at the magnification, m1 will be positive, but m2 will be negative, right? So we can say m1 will be negative of m2. So what is m1? M1 will be height of the, or we can also write this as minus of v1 by u1, and this can be written as minus of minus v2 by u2. Let us put the value. So minus of v1 divided by u1 is minus 20, and that will be minus of minus v2 divided by u2, that is minus 10. Now from this equation, this will give us 2 here, this negative will get cancelled out. So v1 comes out to be negative of 2 times v2. Okay, so we got the relation between the distance of the images from the optical center, and we need to find the focal length. So let us apply mirror formula for both the object distances. So we can say 1 by v1 minus 1 by u1, which will be minus 20, will be equals to 1 by f, and this is also equals to 1 by v2 minus of minus 10. Now by using this equation, we can find the relation between v1 and v2. So let us first find v2. So 1 by v1 plus 1 by 20 is equals to 1 by v2 plus 1 by 10. Now we can write v1 as minus of 2 times v2. So 1 upon minus 2 times v2 minus 1 by v2 will be equals to 1 by 10 minus 1 by 20, which will be 1 by 20. So this can be written as minus 3 by 2 v2. So that's this is equals to 1 by 20. So 2, yes. And from this, v2 comes out to be minus 30 centimeter. Okay, so we can say so so v1 yes, u2 is minus 10, so this distance comes out to be 30. Okay, now let us use this equation to find the focal length. So we can say, so 1 by f will be equals to 1 by minus 30 plus 1 by 10. So that will be, so 30 will be the LCM. So minus 1 plus 3. So it will give us 1 by 15. So focal length will be 15 centimeters. So that is the answer of this question. Now let us see another question. As shown in the figure, a combination of a thin plano convex lens and a thin concave lens and the convex lens used to image an object placed at infinity. So there is an object which is at infinity, and the lights are coming towards this combination, and the radius of curvature of the lenses is 30, and the refractive index of the material for both the lenses is 1.75. Both the lenses are placed at a distance of 40 centimeter from each other. Due to the combination, the image of the object is formed at a distance x centimeter from the concave lens. So we have to find the distance from the first lens, which is a concave lens. So first of all, we have to apply lens maker formula, and we have to find the focal length of these both of these lenses. So let me call this as lens 1, this as lens 2. So for lens 1, so 1 by f1 will be 1.75 minus 1 times, and it's a plano concave, so it will be minus 1 by r, and r is given as 30, right? So it will be negative. So it comes out to be 0.75 divided by 30 with a negative sign, or we can write this as minus of 3 by 4 times 30. So it will be 1 by 10. So it focal length f1 comes out to be minus 40 centimeter. Similarly, for the plano concave, which is also having the same radius of curvature, f2 will be plus 40 centimeter. So we got the focal length of both the lenses. Now if the rays are coming parallel, so they will get diverged, and the image will be formed at the focus. So that will be the focus. That is the first image, which is at a distance 40 centimeter from the concave diverging lens. Now this image will act as the object for the other lens. So we can say the distance of this I1 from the other lens will be nothing but 80 centimeter. Now we have to apply lens formula to find the position of the image. So we can say 1 by V minus of minus 80, because U will be 80 centimeters, so it should be negative. And the focal length will be plus 40. So 1 by V is 1 by 40 minus 1 by 80, so that comes out to be 1 by 80. So V is 80 centimeters. So we got the position of the final image, and this image is at a distance of 80 plus 40 from the first lens, because this is the distance from the second lens. So this is the final image I2, and this distance is 80. So the distance from the first lens will be 80 plus 40, that is 120. So 120 is the answer of this question. Next problem type is based on the speed of the image formed by the lenses. So if we consider, say, a convex lens, right, and there is an object which is at a certain distance, and it is moving, say, towards the optical center, or let me take some values. Let us say the focal length is 40 centimeter and the object is placed at a distance of 100 centimeter, and it is moving towards the optical center with a velocity 2 centimeters per second. So we have to find what is the velocity of the image. So in this question, what we have to do, the position of the object is changing, so we can see the position of the image will also change. So the rate of change of position of the object will give us the velocity of the object, and the rate of change of the position of the image will give us the velocity of the image. So du by dt, that is the velocity of the object, and dv by dt will be the velocity of the image. So let us differentiate the lens formula with respect to time. So that will give us 1 by v square times dv by dt, and this will give us plus 1 by u square times du by dt, and the focal length is constant. Now from this, dv by dt will be equals to v square by u square times du by dt. Now you have to remember this formula, right? So this will be the velocity of the image, and this is the velocity of the object. Now in this particular problem, if I apply lens formula, so 1 by v will be equals to 1 by f plus 1 by u. So 1 by 40 minus 1 by 100. So this comes out to be 200 will be the LCM. So 5 minus 2, that will be 3 by 200. So V comes out to be 200 by 3 centimeter. So if we apply this formula, velocity of the image will be 200 by 3 divided by minus 100 square times the velocity of the object, that is 2 centimeter per second. So this will give us 4 by 9 times 2, so it will be 8 by 9 centimeters per second. So that will be the velocity of the image, and velocity of the image comes out to be positive. It means it is also going in the right direction. Somewhere here we have the image, and it is going in right direction with 8 by 9 centimeter per second, and the distance of the image is 200 by 3 centimeter. Now if the object is moving perpendicular to the principal axis, it is at the principal axis and it is going perpendicular to the principal axis. Now in this case, the u value and the v value will be constant, so height of the image upon height of the object will be v by u. So we can say dhi by dt will be equals to v by u times dh naught by dt. Now this is the velocity of the image, and this will be the velocity of the object. If we are able to find the value of v and u will be given we can use by using the lens formula. We'll be able to find the velocity of the image, right? Now the next problem type is based on the power of lens. Now what is the power? So lens power is nothing but the reciprocal of the focal length, and power will be positive for converging devices. And what are converging devices? It will be a converging lens or concave mirror, and power will be negative for diverging devices. What are diverging devices? Diverging lens and convex mirror. Right, so let us see a question based on this problem type. A biconvex lens of focal length 10 centimeter So focal length is given as 10 centimeter, is cut into two identical parts along a plane perpendicular to the principal axis. The power of each lens after the cut. Let us see. So we have given a biconvex lens, and this is R and this is R. Focal length is given as 10. So 1 by 10 will be equals to mu minus 1 times 2 by R. Okay. So from this we can say R upon mu minus 1 is equals to 20. Now if I cut this lens from the middle perpendicular to the principal axis, then we will get a plano convex lens. So this will be R, and here the radius will be infinity. So here the new focal length f prime 1 by f prime will be mu minus 1 times 1 by R, and R by mu is nothing but 20. So mu minus 1 by R will be 1 by 20. So that will be 1 by 20. So f prime will be 20 centimeter. Or we have to find the power. So 1 by f prime is 1 by 20 centimeter. If I multiply this with 100, we'll get meter inverse. So that is nothing but the power. So it will be 5 diopter. So power will be 5 diopter. So 5 is the answer to this question. Now let us see one more illustration. A convex lens has a power P. It is cut into two halves along its principal axis. Further, one piece out of the two halves is cut into two halves perpendicular to the principal axis. Okay, so this one, these two, like this is the perpendicular to the principal axis, right? Choose the incorrect option from the reported pieces. So let us first find the power of each. If you look at this problem, if you cut it, if you make it into two parts, then the power, or you can say the focal length, will become double, right? If the focal length is getting double, the power is getting half, right? So so we can say for L2 and L3, the power, let us say, is P, and this is P. Okay, power for this lens is given as P, so the power of this lens will be P by 2, and for this lens it is P by 2, and for L1 it is P. So the power of lens L1 is P, so this is incorrect, or this is the answer basically. We have to find the incorrect option. Power of lens L2 is P by 2, power of lens L3 is P by 2, power of lens L1 is P. Right, so option A is the right answer. Now let us see the next problem type, and it is based on the combination of thin mirror which are touching each other, and we have to find the effective power. So suppose we have two mirrors. This mirror has a power P1, this is having a power P2, then the effective power is nothing but the sum of the individual powers. Now let us see an illustration. So here we have given a converging lens which is having a focal length 10 centimeter, and there is a diverging lens which is having a focal length of 40 centimeter. We know that power for converging is positive and power for diverging lens is negative. So for power for the first lens will be 1 upon 0.1 diopter, and for the second will be minus 1 upon 0.4 diopter, and by using this we will get 7.5 diopter, which is positive. So we can say the effective combination is behaving like a converging device. And if you want to find the focal length, we can just convert this diopter, or we can simply just find take the reciprocal of that. It will give us the focal length in meters, then we can multiply that with 100, we'll get the focal length in centimeters. Now let us see a question based on this concept. The effective power of the combination of 5 identical convex lenses which are kept in contact along the principal axis is 25 diopter. The focal length of each convex lens. So we know that 5 times the power of one lens will be 25 diopter. So power of each lens will be 5 diopter. And we have to find the focal length. So 1 by f is 5 meter inverse, or f will be 1 by 5 meter, or you can say it will be 100 by 5 centimeters. So that comes out to be 20 centimeters. So option 1 is the right answer. Now let us see another illustration. The convex lens of focal length 20 centimeter is placed in front of a convex mirror with the principal axis coinciding with each other. The distance between the lens and the mirror is 10 centimeter. A point object is placed on the principal axis at a distance 60 centimeter from the convex lens, the image formed by the combination. So this is the next problem type where we have a combination of mirror and the lenses. The image formed by the combination coincides the object itself, the focal length of the convex mirror. Right, so let us see. So we have given a convex lens of focal length 20 centimeter. This is the principal axis. And there is a convex mirror whose principal axis coincides with each other, right? Right. The distance between the lens and the mirror is 10 centimeters. So there is a convex spherical mirror and the distance between them is 10 centimeter. And point object is placed on the principal axis at a distance of 60 centimeter. There is an object which is placed at a distance of 60 centimeter from the lens. The image formed by the combination coincides the object itself, the focal length of the convex mirror. Right. So what we can say, the image formed by the lens is forming at the center of curvature of the mirror. Only in that case, the ray is hitting the mirror normally. So if this is the center of curvature, let us say this is the ray. After convergence, this ray passes through the center of curvature and then it will retrace its path and the image is being formed at the object itself. So we can say, let us first find the position of the image formed by the lens. So 1 by V minus 1 by U, that is minus 60, and focal length is 20. So 1 by V is equals to 1 by 20 minus 1 by 60. So that will be 3 minus 1 by 60. So it will be 1 by 30. So V comes out to be 30 centimeter. So it means this distance will be 30 centimeter and we have to find the focal length of the convex mirror. So the radius of curvature of the convex mirror will be 20 centimeter. Focal length will be half of that, so 10 centimeter. So 10 is the answer of this question. Let us see another question based on the same concept, mirror and the lens. An object is placed on the principal axis of the convex lens of focal length 10 centimeter. A plane mirror is placed on the other side of the lens at a distance 20 centimeter. So this is 20. The image produced by the plane mirror is 5 centimeter inside the mirror. The distance of the object from the lens is. So what we have given, that the image is being produced 5 centimeter inside the mirror. So that is the image. Right. So this is, let me call this as the final image. And this distance is given as 5 centimeter. So it means the image formed by the mirror will be at 5 centimeter in front of the mirror. So this will be the first image which is produced by the lens. So this distance of the image from the lens is 15 centimeter. Now by applying lens formula, we can find the position of the object. So 1 by 15 minus 1 by U is equals to 1 by F, and the focal length of the lens is given as 10 centimeter. So it will be 1 by 10. So 1 by U is equals to 1 by 15 minus 1 by 10. LCM will be 30, so that will be 2 minus 3, so minus 1 by 30. So U comes out to be minus 30 centimeter. So it should be 30. Now the next problem type is based on chromatic aberration. What do you mean by that chromatic aberration? If we have a white light, so let us, this is the white light, and different colors have a different refractive index for this lens. So that's why they have different point of convergence. So we won't get a unique focus in this case. So this is known as a chromatic aberration. Now let us see a question based on this. When a beam of white light is allowed to pass through a convex lens parallel to the principal axis, the different colors of light converges at different points on the principal axis after refraction. This is called chromatic aberration, right? Option 2 is the right answer. Now there is another concept, another problem type which is based on spherical aberration. What do you mean by that? If you consider a spherical concave mirror, right? So this is a concave mirror. And if we consider marginal rays, right, so even in this, in case of marginal rays, we won't get a unique point of convergence. Now this is known as a spherical aberration. We are not getting a unique image. So how to overcome this aberration? We can use parabolic mirrors, right? So parabolic mirrors are the corrective mirrors that can be used to avoid spherical aberration. Can avoid this defect. So we are done with the problem type associated with lenses. I hope your confidence has improved in lenses part. Now let us see the different problem types in optical instruments. So these are the four types we are going to discuss: simple microscope, compound microscope, astronomical telescope, and the Cassegrainian telescope. So let us see. Okay, right. So to understand that, we should know what is power of accommodation, what is far point, what is the near point or the least distant of distinct vision, or the visual angle. Now the power of accommodation is the ability of the human eye to adjust its focal length, and the far point is the farthest that the eye can see. And in case of a normal human eye, the far point will be infinity, and the near point or the least distance of distinct vision is the closest an eye can see, and it will be 25 centimeter for normal eye. And the visual angle is the angle that the object subtends on the eye, and it gives us the perception of the size of the object. Now let us see the very first optical instrument, that is simple microscope. So suppose if there is an object and we are looking at this object from the least distance of distinct vision, this is 25, and the object subtends an angle of theta naught at our eye. But suppose if I look at the same object with the help of a simple converging lens, which is known as a simple microscope or magnifier, in that case, the same object will subtend a greater angle on the eye, because we are able to place the object closer to the eye, so that's why it will subtend a greater angle, and the image is being formed at 25 centimeter only. So what we can say, the simple microscope is basically increasing the visual angle of the object so that we'll get a magnified view of the object. Now if you look at the ray diagram, so we have given right, so let me first draw the lens here. So okay, right, so lens is there. So this is the eyepiece and this is the aided eye case, where we have placed an object between the focus and the optical center, and we are getting a virtual and erect image of the object. Now the angle that this image subtends on the eye is beta. And suppose if we place the same object at a distance 25 centimeter from the eye, the angle it subtends is alpha. Now the angular magnification is defined as the ratio of beta and alpha, and it comes out to be d by ue. So that is the general formula of angular magnification produced by the simple microscope. Now there are two settings. So one is the normal setting, when the final image is being formed at infinity. So in this case, ua is nothing but fe, and the magnification will be given by d by fe. And this is the next setting is the most strained eye, where the final image is being formed at the least distance of distinct vision, which is d. And in this case, u can be written as dfe upon d plus fe. So the magnification will be given as dfe plus 1. So we can say in case of a simple microscope, the magnification will vary from d by fe to d by fe plus 1. We'll get maximum magnification in case of most strained eye, and we'll get minimum magnification in case of normal setting. Now let us see a question based on this in JEE Mains. So we have given assertion as well as a reason. So let us see the assertion. For a simple microscope, the angular size of the object equals to the angular size of the image. Yes, so that is true. That's what we have seen. Reason: magnification is achieved as the small object can kept much closer to the eye than 25 centimeter, hence it subtends larger angle. Yeah, so that we have just discussed. Yes, so reason is also correct. So we can say both A and R are true, and R is the correct explanation of the assertion. So option 3 is the right answer. Now let us see this question. An object is to be seen through a simple microscope of focal length 12 centimeter. Where should the object be placed so as to produce maximum angular magnification? The least distance of clear vision is 25 centimeter. So here maximum angular magnification happens when the final image is being formed at least distant or distinct vision, or we can say the maximum uh, or you can say, let me just quickly write here the diagram. So let us say this is the focus, and somewhere here we have placed the object, right? And its image is being formed somewhere here. Now this image will be formed at least distance of distinct vision. So in this case, we'll get the maximum angular magnification. So we have to find the position of the object. So we have to find u. So we can apply lens formula. So 1 by v minus 1 by u is equals to 1 by f. And v in this case will be minus d minus of u, and it will be 1 by f. And the focal length is 12. So 1 by u will be minus of 1 by 25 minus of 1 by 12. So this comes out to be minus 37 upon 300, right? So u comes out to be minus 300 upon 37 centimeter, right? So that should be the answer of this question. Now let us see the next problem type, and it is based on the compound microscope. So what happens in case of compound microscope? We have two converging lenses. This one is known as, this one is the objective, and this one is the eyepiece, which is closer to the eye. Objective is closer to the object, right? And in this case, the aperture of the eyepiece is greater than the aperture of the objective. Now, this objective lens formed, the object is placed beyond focus for the objective, and its real and inverted image is being formed. And we'll make sure this image is being formed between the focus and the optical center of the eyepiece. Now, this intermediate image will act as the object for the eyepiece, and we'll get a virtual and erect image, final virtual and erect image. Now, let us see the ray diagram. So in this case, the angular magnification will be given by V naught by U naught times D by UE, where V naught is the distance of the intermediate image from the objective lens, and U naught is the distance of the object from the optical objective lens, and D is the distance, it is the least distance of distinct vision, and U is the distance of the intermediate image from the eyepiece, and V is the distance of the final image from the eyepiece. Now, if you look at this magnification formula, it is nothing but the product of linear magnification produced by the objective lens times the angular magnification produced by the eyepiece. And the length of the optical compound microscope is given as V naught plus UE, which is nothing but the distance between the two lenses. So this you have to remember. Again, we're going to study two settings. So the normal setting, the final image is being formed at infinity. So in this case, UE will be equals to FE, and the magnification will be given as V naught by U naught times D by FE, and the length will be V naught plus FE. In most strained eye, final image will be at the least distance of distinct vision, and in this case, U will be DFE by D plus FE, and magnification will be V naught by U naught times D by FE plus 1, and the length will be V naught plus DFE upon D plus FE. Now let us see the question based on this concept. A compound microscope consists of an objective lens of focal length 1 centimeter and an eyepiece of focal length 5 centimeter. So objective lens has a focal length 1 centimeter and eyepiece is having a focal length 5 centimeter, and the separation between them, so L is given as 10 centimeter. The distance of between an object and the objective lens at which the strain on the eye is minimum is n by 40 centimeter. Find the value of n. So strain is minimum means we are talking about the normal setting. So in normal setting, the final image is being formed at infinity. So if I draw the ray diagram, or if I show the lenses or the object and the images, so we can say in this case the image is being formed at infinity. So the intermediate image will be at the focus of the eyepiece. So this focal length is 5 centimeter, and we can say the distance of this intermediate image from the objective is also 5 centimeter, because the length of the instrument is 10 centimeter. Now we know the position of the intermediate image from the objective, We know the focal length of the objective. Now we can use length formula to find the position of the object. So 1 by v naught minus 1 by u naught is equals to 1 by f naught. So it will be 1 by 5 minus 1 by u naught is equals to 1 by 1. So from this we can say 1 by u naught will be 1 by 5 minus 1, which is minus 4 by 5, 1 by u naught. So u naught will be 5 by 4 with a negative sign. And this is given as, so 5 by 4 is nothing but n by 40. So n comes out to be 50 centi, no, not 50 centimeter, just 50. Right, so now let us say the next problem type or the next concept, that is the astronomical telescope. In case of astronomical telescope, the objective will be having a large aperture, so to have a good resolution in the image. And in this case, if the usually we use astronomical telescope to study heavenly bodies, so they are quite far. So we can say the rays will be parallel to the will be parallel to each other, and the image is being formed at a point on the focal plane. So that will be the intermediate image, and it will be formed at the focus of the objective, right? So if you consider magnification, it comes out to be f naught by ue, that is the general formula. And the length of the astronomical telescope will be f naught plus ue. Now there are two settings. So first setting is more where the final image is being formed at infinity. So the magnification will be f naught by fe, and the length will be f naught plus fe. And in case of most strained eye, the distance of the intermediate image from the eyepiece will be dfe upon d plus fe, and in this case the magnification will be f naught by fe times 1 plus fe by d, and the length will be f naught plus dfe by d plus fe. Now let us see the question based on this. In normal adjustment where the strain is least, for a refracting type, that is based the lens, the telescope that we have just discussed, the distance between the objective and the eyepiece is 30 centimeter. So we have given L as 30 centimeter. Find the focal length of the objective when the angular magnification of the telescope is 2. So normal setting is given, and in normal setting magnification is given as f naught by fe, and the length is given as f naught plus fe, right? And magnification is 2. So f naught is 2 times fe. So if I substitute this in this equation, we'll get 3 fe equals to 10. So fe comes out to be 10, right? So this is 3 fe equals to 30 and f equals to 10 centimeter. Now we know fe, and we have to find the focal length of the objective. So objective focal length will be 2 times 10, it will be 20. So option A is the right answer. Now the fourth concept in optical instrument is Cassegrainian reflecting type telescope. Here we use mirrors instead of lenses, and this will be a parabolic mirror, right? And this is the secondary mirror. So the light which are coming from the heavenly bodies, they reflect from the objective lens. This is the objective lens, and then after reflection from the secondary mirror, we'll be able to see the image with the help of eyepiece. Now what you have to remember, even in case of Cassegrainian reflecting type telescope, magnification is f naught by fe, where f naught is the object focal length of the objective mirror, and fe is the focal length of the secondary mirror. And the magnification in most strained eye will be f naught times 1 plus fe by d. So these magnifications are similar to the refracting type. Now let us see the question. In a refracting type telescope, the secondary mirror is used to right. So its main purpose is to move the eyepiece outside the telescope tube, right? So can you see? This eyepiece is outside the telescope tube. So that's why we use this secondary mirror. So we are done with the different problem types in optical instruments. Now let us see the last part, last block, where I'm going to discuss some experimental questions which can be asked in JEE Mains. Now the first one is, so these are the three types. Let us discuss these types one by one. Let us see the first experiment where we have to find the focal length of a convex lens. So here we have given a convex lens which is having a focal length f, which we have to calculate. The magnitude of the object distance x and the image distance y as measured with reference to the focal point of the lens. So from the focal point we are measuring the distances, and y-x plot is shown in the figure. The focal length of the lens is, so here we're going to use Newton's formula, which is nothing but x times y will be equals to f square. So we have to use this relation, right? So if you look at the point C, we can say the value of x is 20 centimeter and for value of y will be 20. So if I substitute these values, so 20 times 20 is equals to f square. So we can say focal length is nothing but 20 centimeter, right? So just remember this formula. So now if you look at this next experiment, here we have to find the refractive index of a glass slab. So if I show this in a diagram, so here we have given a glass slab and we want to find the refractive index of this glass slab with the help of a traveling microscope. So what we're going to do, so let us first read the question. So in finding out the refractive index of a glass slab, the following observations were made through the traveling microscope. 50 vernier scale division is equals to 49 main scale division and 20 division on the main scale in each centimeter. So what do we mean by 20 division on main scale is equals to each centimeter is 1 centimeter by 20 is 1 main scale division, right? And 50 vernier scale division is equivalent to 49 main scale division, and 1 main scale division is 1 by 20 centimeter. So from this we can say 1 vernier scale division is 49 by 50 times 20 centimeter. Now if you want to find the least count of the instrument, so the least count is nothing but 1 main scale division minus 1 vernier scale division. So this comes out to be 1 by 20 centimeter minus 49 by 50 times 20. So this can be written as 50 minus 49 divided by 50 times 20. So this will be 1 upon 1000 centimeter. So it will be 0.001 centimeter. So that is the least count of this instrument. Now let us see some of the readings. So for mark on the paper, so basically what we do in this case, there will be a paper on the floor right here. So let me call this point as A. So the first reading corresponds to the mark on the paper when there is no slab there, right? If there is no slab, we can measure the distance of point A from the microscope. Okay. So let's say we have found, so this is the distance of the point A from the microscope. For mark on the paper seen through the glass slab, if you see A with the help of the glass slab, then there will be some apparent shift in the point A. Then we'll measure, let us say, the point B due to the shift. So this measures point A, this measures point B distance from the microscope. And for powder particle on the top of the surface of the glass slab, so if we consider point C, will this third reading will give us the position of the point C with respect to the microscope. Now the refractive index, so what we're going to do here, we have to apply the apparent depth formula. So apparent depth, so original depth of A will be AC, right? So it will be nothing but the difference of the reading A minus C, that is the original depth, divided by the refractive index of the glass slab, and that should be equals to the apparent depth, and apparent depth is nothing but B minus C. Can you see? B minus is the apparent depth. Now what is the value of A? So let me just remove this diagram. Right, so reading A, it can be, we can find this as one main scale reading, or main scale reading is 8.45. So it will be 8.45 centimeter plus vernier scale coincidence. Vernier coincidence is 26. So that will be 26 times the least count, which will be 0.001. So it will be 8. Let me keep it like this only, right? So this will be 8.45 plus 0.026 centimeters. And B will be 7.12 centimeter plus 41 times 0.001 centimeter. So that will be 7.12 plus 0.041 centimeters. And C will be 4.05 plus 1 into 0.001 in centimeters. Now mu will be nothing but A minus C divided by B minus C. So A minus C will be 8.45 minus 4.05 plus 25 times 0.001, right? Divided by B minus C. So B minus C will be 7.12 minus 4.05, and it will be plus 41 times 0.040 times, right? 40 times 0.01. So that will be the refractive index. So let us simplify this. So the answer comes out to be 1.42 by simplifying this. So it will be option 3. That is the right answer. That is the next type. Here we have to find the radius of curvature of the convex lens. So here we have given the graph between 1 by u and 1 by v for a thin convex lens in order to determine the focal length is given, and the refractive index of the length of the lens is 1.5, and its both surfaces have the same radius of curvature. The value of r will be, now let us see the diagram. So here we have 1 by u on the x-axis and 1 by v on the y-axis, and if you apply lens formula, that is 1 by v minus 1 by u is equals to 1 by f, or this can be written as mu minus 1 times 2 by r. Now this right hand side is positive, right? And here we have 1 by u on the negative x-axis. So we can write this as 1 by v plus minus 1 by u equals to mu minus 1 times 2 by r. Got it? Okay. So what we're going to do, let us consider one of the case. So if 1 by u is minus 0.1, then what is 1 by v? That will be 0. So if I put it if I take this particular value, so that will be 0, and this will become plus 0.1, and it will equals to 1.5 minus 1 times 2 by r. Now from this 0.1 is equals to 0.5 times 2 by r, and this will give us 1, so r comes out to be 10 centimeter, right? So the answer will be 10 centimeter. Okay, just there is a small correction here. It is not mirror, it is lens, right? So here I conclude the session. So we have covered all problem types, and I'm pretty hopeful if any question comes from this chapter, you'll be able to answer that in JEE Mains 2025. If you find videos of this series useful, so it is highly recommended for you to join PracBee's revision program. So in this program, we're going to cover 10 blocks in 10 weeks, and we'll give you a target of 1 chapter per day, and we'll be able to cover all relevant chapters by the first attempt of JEE Mains. And how you can join this revision program? By clicking on the link given in the description. And one more thing you can do, please drop a comment. Let us know what else we can do for you to make this series better. Thank you.